Inspiration 4 is go for launch. Punch it, SpaceX.
Commander calling down.
30 seconds.
Punch it, SpaceX.
T-minus 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Ignition. And liftoff. So thank you. Go Dragons. Go Falcons. Godspeed Inspiration 4.
Welcome to the SOE 22 Space Ocean Nerd Insights. This year, focus on how bio, geo, and tech come together to discuss the current frontier of space exploration. Whether you're joining us from the School of Engineering in Porto or elsewhere via our YouTube channel, get ready for an exciting event. We have just watched a video from Inspiration 4 mission, the world's first all-civilian mission to orbit. This mission marks the beginning of a new era in space exploration and explains why we are here today. Space is meant for all. Therefore, prepare yourself to dive into the deep sea, walk on Earth, and fly out to space and deep space. A handful of experts will come together to talk to you through state-of-art research across several fields of knowledge fitting into space exploration, space medicine, georobotics, aeronomy, space Earth-sea interactions, space resources, or remote sensing, just to list a few. We sincerely acknowledge our sponsors and partners for all your support. Without you, this workshop would not lift off into space. Also, special thanks to SpaceWatch.global and Mark Blum for covering today's event. Without further ado, let's welcome on stage our host, Maria João Viamonte, President of the School of Engineering of the Polytechnic Institute of Porto, to officially open the SOE 22 Space Workshop.
Thank you. Good afternoon. It's a great honor for me to be here in this opening session of this important workshop with the opportunity to be all together again, what is fantastic, I think. It's also a great honor for us to welcome you here at our school. This year we celebrate 170 years, and I have also a video to present all of you our story. Thank you.
A humanidade sempre se moveu pelo progresso na procura do desconhecido. É essa a sua história e é nela que se insere a engenharia como um dos grandes pilares dessa ambição. Esta é a premissa que nos guia desde o primeiro dia. Nos idos de 1852, nascem as bases do Instituto Superior de Engenharia do Porto, com a Escola Industrial do Porto, uma das bandeiras do primeiro sistema público de ensino industrial. Anos mais tarde, em 1864, efetua-se uma ampla reforma e expansão do ensino industrial. A Escola Industrial torna-se Instituto Industrial do Porto, formando mestres, condutores e diretores de fábrica. Em 1974, no pós-revolução, os institutos industriais convertem-se em Institutos Superiores de Engenharia. É no âmbito deste reconhecimento que os institutos são inseridos na estrutura do ensino superior, evoluindo o Instituto Industrial do Porto no atual Instituto Superior de Engenharia do Porto. Em 1989, o Instituto Superior de Engenharia do Porto é integrado no subsistema de ensino superior politécnico, passando a fazer parte do recém-criado Instituto Politécnico do Porto. Aos dias de hoje, o Instituto Superior de Engenharia do Porto, ISEP, continua a ser uma referência a nível nacional e internacional na formação de profissionais altamente qualificados nas vastas áreas da engenharia. O ISEP disponibiliza um conjunto de licenciaturas e mestrados que vão desde as áreas mais tradicionais da engenharia até às áreas mais emergentes. A investigação, o desenvolvimento e a inovação são uma clara aposta do ISEP, que incentiva esta prática na sua comunidade académica através de um conjunto de ações e programas que projetam o futuro no presente. O ISEP conta com um corpo docente e não docente altamente qualificado e motivado, o que permite formar os engenheiros do amanhã como profissionais capazes de conceber, projetar, implementar e operar sistemas de engenharia de última geração, incentivando assim o pensamento individual, o sentido crítico e o trabalho em equipa. O campus é composto por 9 departamentos, 10 centros de investigação, 7 centros de prestação de serviço, biblioteca, um museu que faz parte da Rede Nacional de Museus, um centro de congressos, uma agência de viagens e uma agência bancária. É um campus pronto para receber todos os que procurem na engenharia o seu futuro. Uma escola moderna, onde a qualidade está patente em todas as atividades que desenvolve. Uma escola alinhada com os ideais de sustentabilidade, que adota medidas que contribuem para garantir um modelo integrado de gestão, assente no respeito pela vertente económica e no fomento da responsabilização social e ambiental. Tudo isto permitiu ao ISEP ser a primeira instituição de ensino superior a receber a distinção Coração Verde, atribuída pela LIPOR. O ISEP participa nas grandes redes internacionais de escolas de engenharia, permitindo-lhe estar exposto a culturas, tecnologias e sociedades diferentes e, simultaneamente, ter uma visibilidade internacional significativa. O ISEP celebra 170 anos. 170 anos de progresso, ambição e de procura incessante pela excelência. 170 anos de olhos postos no futuro. A evolução continua e nós estaremos cá para fazer parte dela. Instituto Superior de Engenharia do Porto.
Thank you, Maria João, for the video. So now we are ready to take off. The first stop of our journey is the space ecosystem communication and outreach. And to get us in the right mindset, let's listen to Adil Gonzalez, a science researcher, educator, science astronaut, candidate program graduate, POSUM 13 ambassador, and STEM coordinator.
Hola, Portugal. Hola, Yvette. Hola, Aaron. Hola, Jason. My name is Dr. Adil Gonzalez-Riccio, and I am proud to be part of Project POSUM, and I'm also a POSUM 13 ambassador. I am a molecular geneticist, developmental biologist, and I study nematodes. And the reason why I use nematodes is to study genetic disorders and behaviors that are similar to humans. And I really believe that using microgravity may be a tool in using therapeutics more effectively. Such an exciting time as more and more citizens are now heading into space. The innovations that will result will be outstanding. And in the next 10 years, in collaboration with new emerging space nations like Portugal, literally the universe is our limit. Welcome. Thank you. Take care. Bye.
Thank you, Adil, for recording this message for our guests and audience. Let's now call on stage one of our amazing chairs. I am pleased to introduce you to Yvette Gonzalez, Head of International Collaborations and Strategic Initiatives at the International Institute for Astronautical Sciences. Before taking over the chairing of today's event, Yvette will be sharing her views on shaping access to the space and humanity ecosystem. Yvette, I turn it over to you.
Thank you. Hi, everyone. Good morning, good afternoon, wherever you are in the world watching. Thank you for having me here. It is an honor and a pleasure to share the stage with experts and to also share what we've been contributing with the world. So all of you online, welcome. Today I'm going to be talking about what our institute is working on, and this is the International Institute for Astronautical Sciences. And today, I very intentionally said space and humanity because we were a group, like any group, like INISTEC, ICEP, and all the groups have come together today, where you have groups of passionate and very dedicated dreamers. And Dr. Aaron Prasad, who's here in the audience, you'll hear from him later, but he always reminds us that everything that we can think of everything that we can conceive, we can make happen. We can make it possible. And that's what we all work to strive to do. So we really want to transform what it means to be in the space industry and how that matters here on Earth. That we're not just sending experiments for the sake of putting them in microgravity, that they matter to how we innovate here. So we had a team in 2012, and even before, who conceived of what are the things that we need? What is happening? Why is it so important to be part of building and growing and evolving an ecosystem for space? And how does that matter for Earth? What we recognized very early, and our team recognized, was that there needed to be a paradigm shift. And I think it still exists and evolves today, but it was really, how do we remain credible with what we're doing? How do we make it relevant for what you're doing in your work, and how does that matter? And in a place where space is still a privilege, where it is still expensive, where it is still for a few who have access, how do we bridge that gap? So that was kind of the genesis and the origin story for how we conceived an institute to do work together. And also, we are facing a climate catastrophe. And instead of shying away from that, how do we embrace our facilities, our research, and our science to address that together? So the origin of our group is Dr. Jason Reimmuller, who is here today with us, came together after working at NASA and wanted to specifically work with researchers, even non-traditional backgrounds, non-traditional countries and nations. How do we work together to bring science to a new head? And how do we offer that for atmospheric research, climate research, ocean research, and the whole spectrum of what we're going to discuss today? And he did that quite organically, I think, bringing together people who cared, who were passionate, and had the ability to dedicate their time and their professional careers to contributing to the science. It's also important that what we do remains equitable. And I know that word is very popular, and I know a lot of people say they have equity or they're being equitable with their work. But the intention is that our teams involve women, men, young, and even those with a lot of experience to the same table. And in doing that, we're offering generations the ability to collide, right? So when you have generations coming together, you're sharing vast knowledge and tradition, and you're introducing new technology. So we put together, actually there's 3 pillars, but the first one that underlies all of them is science. But we do education, research, and outreach, which is very critical today. So this is one of our facilities. We have a neutral buoyancy lab, so this is what you're seeing here. One of our first underwater exercises was earlier last year. So in our education framework, we're working to develop courses that are run by instructors who are really well known in the industry, have history with organizations like NASA, and who bring together really novel ways of teaching. And we call that experiential learning. So much like the institutes here, it really involves being in person, engaging together, and ensuring that everything that we do in theory, we immediately practice. So you'll see a lot of photos maybe on our website or in the presentations the remaining day that have campaigns in the field, in microgravity, in geologic, Apollo testing sites. And that's because we take that framework and we make sure that we do it in person. The other thing that's really important is that we develop our own curriculum. And so our instructors, they make sure that the curriculum suits our student body, the facilities that we have access to, and that it's very unique in making sure that there's non-discriminatory application process for that. So that we say, we know everyone who wants to apply, we know what they have access to, and we offer a very high level, high fidelity experience, and we don't block anyone from having access to that. And it's not very easy to accomplish. So a lot of work goes into making sure that this remains open for everyone. This is Dr. Rui Mora in our geological course at the original Apollo sites for astronauts trained for geology. And it's important that when we bridge our education to research, that the research is really the foundation for everything else that comes after. So you don't take a class, you graduate and you finish. You are part of a cohort who learns together, acts together, researches together, and then publishes together. And it's very encouraged that that spectrum of ability, that experience continues, it doesn't end. We really have this kind of flagship approach, and we like to share that openly. So if you look on our website, you will see that we actually lay out the curriculum so you know what you're getting into. But you have the ability as part of our institute to also shape what that's going to look like. The research also is important and vital to publications. And we want to make sure that we're part of a dialogue, a conversation, that it means something when we do something. And if it doesn't, we go back and we do it again. Or we use a different way to do it. And we encourage curiosity, which is, I think, what we're all doing here today, is that if you are curious about space or Earth or the oceans and all of it together and how it's interconnected, it's a very, very, I would say, conducive environment to making sure that your questions can be explored together. And here for our outreach impact, which is our last pillar. We developed, I think in 2018, there was a recognition that if we can do it, why can't anybody else? We individually, after a microgravity flight or after being in a spacesuit, thought, I feel like an ordinary person. I come from a country that never has seen this. But if I can do it, then how can I help other people do it? And so we developed Space for All Nations, which was one of our initiatives. And that's the one that we are now working actively to create bridges with other emerging space nations. And Space for All Nations was one tier. How do we enable more countries to become involved? Possum 13, which you heard Dr. Gonzalez mention in her video, is for young girls. And it was in honor of the Mercury 13, so that young girls and women who aspire to be in STEM have role models and accessible mentors that can help them get there. And then we have Out Astronaut. And Out Astronaut is for the LGBTQ plus community so that they also can have someone representative in the industry and that there's a path to having somebody research with us who represents underrepresented groups. So through all this outreach, we only imagine that we might help maybe one person that identifies with us, but it ended up being a very powerful tool to share what we do, how we do it, and then inviting and enabling access to information and opportunity. So it's very actively and intentionally opening doors and allowing people to have an opportunity. So there is so much more. And I mean, I can talk for days about it, but we have an exciting agenda ahead. And it is my real privilege to be here today. Thank you for inviting me. I'm happy to co-chair, and I would love to introduce you now to my co-chair, Ricardo Conde, who is the president of the Portugal Space Agency, and he will be coming up to do a presentation on Space 2.0, the Space 2.0 race. So welcome.
Thank you very much. This event is quite well prepared, you see. I have a script here. All the things are here. So I need to follow this. Thank you, José Manuel Mendonça, Maria João, my colleagues, Rui, Ana, Miguel, where is Miguel? There, and so many colleagues that I know. It is really an honor to be here, and we have seen these last, Luisa is there. We have been seeing these last 2 weeks, so many events about space, right? We had here the UN Ocean Conference, and you know, one of the outcomes was about space. How space can deliver, how space is needed to tackle one of the main problems that we have, to take care about our planet and also to take care about our oceans. And more, space is engaged in this big adventure. So I will start to share with you a video, 3 minutes, I suppose. I need to press here. Yeah? And this is, I don't want to say this is a corporate video, but it's something to let you know what we are doing, and particularly then I will follow my ideas about some topics. And these topics are, of course, related with the sustainability and how space is really do the job for sustainability.
Portugal is a country of dreamers whose dreams never cease, of explorers who aspire to reach further. Ferdinand Magellan's circumnavigation is matched by man's arrival on the moon.
It's one small step for man, one giant leap for mankind.
Portugal was at the forefront of the evolution of astronomy and navigation instruments, connecting us deeper to the planet we inhabit. Today, space is what motivates us, and exploring it gives us technology that we use daily in schools, agriculture, civil protection services, and many others. Space is in our aspirations. Space is what unites us, and at the Portuguese Space Agency, we want to make Portugal an actor of change, promote space as the home we all belong to, one we must protect. The oceans, 70% of our planet Earth, are a precious resource that now, more than ever, we must take care of. The Atlantic constellation will allow us to comprehend, preserve, and enjoy the Atlantic, promoting sustainability and knowledge, bringing Portugal closer to many other nations with their roots in the sea. The digital planet supports the creation of a multi-platform of Earth observation data. Creating an ecosystem of connectivity through quantum technology will complement global growth by contributing to the development of the Atlantic and the outermost regions. We want to lead innovation using projects such as the Santa Maria Spaceport and Space Rider in Azores. We promote a scientific culture based on technology, research and development among young people. In 2020, we challenged university students to launch rockets in Portugal in the first European competition of its kind, the European Rocketry Challenge, EUROC, a competition with a future in Europe and the world. Since 2000, we have participated in missions of the European Space Agency, where we are increasingly present. Our contribution involves the sustainability of space operations, the cleaning up of our planet and of space, the knowledge of the universe we live in. There are several Portuguese involved in these missions. With our eyes set on space, we contribute to the country's development, creating jobs and strengthening diplomatic ties. As explorers, we have new goals. By exploring other galaxies, we try to reach the sun. This is only the beginning. Our work and commitment will not stop. On the contrary, Portugal Space wants to reduce the space between us for the benefit of all. We create bridges, promote scientific research, innovation, technological advances. We unite sectors. We bring worlds closer together. We recover the spirit of the explorers, sharpen curiosity and the impetus to go beyond. We make space your space, our space, in a shared dream.
So this is the perspective what we are doing, but there are, let's say, common words on this. This is sustainability and how space should deliver. And this is the point. We are approaching a moment that we have some kind of hope in the science and technology to give some answers to the problems that we are living today, right? I think all of us, we have this quite latent feeling that we are really in a crossroads of our existence. And there are so many dimensions. Of course, one of the dimensions is this problem about the climate change. There are so other many problems, particularly the risks that we are facing, a new space race that we are living today, because we are living a new space race. And there are several dimensions. And space has been an inspiration. We are looking, and particularly Miguel for sure will explore that, looking to the stars and also to understand the main answers to our big questions. What we are doing here, and particularly what are we are an interplanetary species. Are we prepared to go to know our neighbors in the cosmos? And this is something that probably the science and some answers that we are looking for science and the new discoveries that particularly some new technologies like the James Webb Telescope will open the window to have these answers. And this is the challenge that we have for space. But space is more than this. And nowadays, space is also a new arena for economy. And let me just spend some minutes on this. We are, let's say, living a moment, a very complex moment, particularly to understand what will be, let's say, the market, what we call new space markets. Nobody knows. This is the right answer. We don't know in 4 years. We know the trends, of course, but we don't know if the market itself, the space market, will be a dream for making business. So you see many constellations, they are launched. You see Starlink, this crazy idea about thousands of satellites to provide basic service like internet, like know everything at each moment where we are, what we are doing, Earth observation, video. And this is one of the scenarios, the scenario of the free market, the liberal market, probably with some kind of regulation. We don't know. This is what we are trying to engage all the nations today. But the other point, which is important, probably we can think in the second scenario. You remember the dot-coms, the one we were in the 2000. We thought that probably we all here and all my colleagues at that time probably will be working in the future. We were in 2000 in the dot-coms companies, but at the end there are 5, 10 companies that remained. So probably the second scenario for space probably will be a game of titans. Probably they will stay 4, 5 big companies and they dominate the market. This is a scenario. But there are another scenario, and this scenario is this third scenario concerns us, particularly to develop science and technology, which is the militarization of space. This is another scenario. Should we have police on space? You know, we are today talking about, normally, the traditional technologies. We are talking about ground-to-space service or space-to-ground service. Now we are starting to change our idea, is space-to-space services. We are changing this idea to what we call it in-orbit servicing. New things, they are produced in space, and they are serviced in space for space. And this is your new paradigm. But this depends on these three main scenarios. But meantime, we need to take care of what we have here. And what we have here is our home, is Earth. And this is the main concern. Probably we don't have time to take care about our home. And I think we need for that a perspective. And the perspective, sometimes a position or point of view different that we have today. We are really concerned day by day in our day life. But if we see ourselves, and this is really a picture that gives us our importance in the cosmos. Look, we are nothing. And this was in the 1990 by Voyager. This gives us our importance in the universe. So look again. That's home. That's us. Probably you recognize that. This is a Carl Sagan, right? And now, if you look this in this perspective, probably we need someone, ourselves, to save from ourselves. So we are really in a trouble, in a crossroads, and you need to take some actions. And particularly, look what, at that time, on the 70s and the 80s, I think some persons here, we need to stop. Yeah? Okay, 5 minutes. I need to run now. Look, this is what we think that we were into the end of century. In the moon, because we destroy the Earth. You see the Earth there. So we escape from the Earth to live in the moon. This is what was our understanding at that time. And this is where we saw in the movies on the 70s, I remember particularly this. And today, the perspective is the same. Probably someone will talk about how difficult is going to the moon. It's really an adventure for one country like the US. This is Mars, and this blue, our planet. It's quite easy to move from one side to another side. And this is probably a geologic moment that we are crossing. Probably it's an anthropogenic moment that we are living. Probably are both. And look at this. I really like this picture. These are not plastics. This is the dots to simulate or to get an information about how we are connected. We have one world. And if you see this, the problem that we are doing to our oceans with the plastics, satellites can play a role to better understand what we are doing. But we know what we are doing. And the big problem, what we did in our planet, we are doing in our outer space. And this is another problem. But we are very clever to transform this in the business. You see what's happened on the garbage, the waste on the 90s in Italy. They transformed this in a big business. This is an opportunity also. But this is a problem. This is a problem, the footprint of the man. Look at this. 60s, when we start the race, space race, on 2030, there will be more than 100,000 satellites, operational satellites flying, providing service flying the Earth. How can we regulate it? How can we create international cooperation to establish the space traffic management worldwide? This is a big problem. We did on the seas. We did to regulate the boats, the shipping, and the seas. We need to go forward with this kind of problem. And look, I will move fast. Look what is the future of space exploration. If we are thinking to go to spaces, to explore the space, this is the problem. Probably we are living some kind of cosmic lockdown, or cosmic confinement. We are trapped ourselves in our planet. This is the problem. And if we are, and if we have some ambitions to space exploration, this is difficult, how to do it. And I really share with you one of the things that should be our main ambition. We need to have data together with artificial intelligence, supercomputing, to get some precise models of the Earth in the several dimensions, in the oceans, in atmosphere, and also in the interactions between ocean and atmosphere for climate change. And for that, we really need a truly open data policy for Earth observation. I will share with you this video. I hope that we can play. This is an amazing video. I saw this the first time in the Global Innovation Summit. This is what we want to have some kind of digital twins for the oceans. Look at this. If we will be well succeed to get this information, the several domains, I think we can have the models to better understand our planet. Look at this. We are all connected. This is amazing how the rivers flows in the oceans. This is what we need for a really open data policy for our globe in several dimensions. This is one of the dimensions for ocean. And this is possible only if we get all the sensors combined in the data fusion to explore as the models. We need models to understand what we are doing. Probably what we are doing, we can just wash our hands and everything will be okay, right? So I conclude here to see this picture, and please have a look at this picture. One of the main problems that we are facing is losing our biodiversity. And particularly, we are continuing to washing our hands, right? And if you see here, be sure to wash your hands and all will be okay. In the meantime, the waves are coming. We are really facing a big problem, and I am really convinced that space can give an answer, and we need space, and we need the data coming from the space, and we need the models, and we need to act. This is time to act. And thank you very much. Let's continue our journey. So I'm pleasure to introduce the next topics today: the cosmos, the moon, Mars, and beyond. And this is Armin, research scientist of NASA Jet Propulsion Laboratory, California Institute of Technology. Okay, it works.
Hi, my name is Armin Kleinbild. I'm a research scientist with the Jet Propulsion Laboratory, and I also direct aeronomy research with Project Possum. I'm located here at ISAS, the Institute of Space and Astronautical Science in Japan, where I work on the Akatsuki Venus Climate Orbiter mission. And you can see a model of the Akatsuki spacecraft over here, and the real one is in orbit around Venus and has been there since 2015. I think the next decade will be very exciting for space exploration. I expect frequent launches to happen with reusable suborbital launch vehicles in order to conduct microgravity research and aeronomy research from a suborbital platform. We will see the return of humans to the moon, where we will have crewed missions, landed missions with crews on the moon for the first time in more than 50 years. We will try to keep ongoing missions going, like Akatsuki here in Venus orbit, or several Mars orbiters and rovers that are orbiting or operating on the Martian surface. In addition, we will conduct sample return missions in order to collect samples from the Martian surface and from the surface of the Martian moon Phobos, launch them into space and bring them back to Earth so they can be analyzed with equipment that we have available here on Earth. Farther out in the solar system, I would expect an orbiter mission to the ice giant Uranus to happen. This is the only type of planet in the solar system that we have not investigated yet with an orbiter mission, so this is a very high priority for the space exploration and space community. So I think there will be a lot of exciting things going on in space exploration in the next decade. I hope I'll be part of some of these endeavors, and I hope you will be too.
This is on. Well, we've heard a lot about where we are and where we want to go. And it's been very exciting. As you saw, Armin is also one of our instructors, so it was great to have a message straight from NASA JPL. I wanted to let you know there will be a Q&A at the end of the session, so we'll let you know when that happens. But for those of you in the room and for those of you online, if you have any questions online, feel free to put them in the chat, and then we'll get to them. And for you in the room, we will come to the Q&A, and we will let you know when you can offer your question. Next, we have somebody very exciting. I'm not from Portugal, but I have heard. We have Miguel. He is currently the host of A Última Fronteira, a program on the latest news about astronomy and space exploration. And it's broadcast by a national broadcaster here in Portugal, RTP. Miguel works to make complex information about space science accessible to everyone. And today, Miguel will tell us what needs to be done to enable the future that we envision regarding space exploration. So please welcome Miguel Gonçalves.
Thank you so much. It's an honor and a pleasure to be here with you. I know that I only have 20 minutes, and I'm trying to do that. I always think about how can I understand the minutes I have comparing to the program that I host in the public television. So I have two programs, 20 minutes to speak about the cosmos. I don't have solutions or great answers. I'm just going to tell you what are the state of the art in some of the aspects and the news that probably you all know about. I love these lines that you can find in Citadel, the book written by Saint-Exupéry. As for the future, your task is not to foresee it, but to enable it. That's what you are doing. You are enabling the future. You are not foreseeing that. You can rest that for the astrologers. So, since this is a workshop about space, the ocean, and Earth, I'm going to start by looking for a perspective, an astronomy perspective, about water. Probably you don't know this, especially in the summer when you go to the beach and you see that vast ocean in front of you. But astronomically speaking, Earth is considered a dry planet, a very dry planet. When we consider the total volume of our planet and compared with the volume of water, it's excluding ice, you see that Earth has only 0.12% of water. Let's compare it to other places in the solar system, to some of the moons and planets. Look at Enceladus, a moon of Jupiter. 20% of liquid volume of water. Look at Ganymedes, 46% of water. So this is astronomy telling us that water in our planet, it's much more precious than probably what we thought. Well, before you saw this slide. And so this is science. And let me tell you what astronomy is for me. Astronomy is the best scientific approach to give us the context about space, time, and matter. It's finding who we are in the context of the cosmos. So I'm going to address some key points that Ricardo also told us, but I'm going to speed it up. There is an interesting line idea that Carl Sagan said in Cosmos. I think that we are going to speak a lot about Carl Sagan in these next talks. And he said, if you remember, that there are more stars in the universe than grains of sands in all the beaches of the planet, of our planet. Well, I tried to make some very small calculations about that, and it's true. We have approximately 10 sextillions stars in the universe, a very sexy number, and compared to the 5 sextillions of grains of sands that there are in our beach. But please don't be very optimistic to go in the near term to one of the stars or even to the nearby stars. I present here some proportions. I know some of them are from science fiction, but nevertheless, the real conclusion is that no, even with our best technology that we have today, there is no way that we can go, well, fast enough for our nearest star. And even when we talk about time, we know that we are a very, very recent invention of the cosmos, as Sagan told us in the so-called cosmic year, when the 1st of January is the Big Bang, and we appear there. The last 500-600 years of humanity are there in the last second of this year. So, what else can astronomy tell us about this cosmos that surrounds us? Well, this. We are a species that know for sure, that knows very little, very, very little about the cosmos, what the cosmos is made of. We know now that approximately 68% is something called dark energy, 25% dark matter, and 5% ordinary matter. Well, we know a little bit more about ordinary matter, but dark energy and dark matter, we have no idea, not the slightest idea of what is made of. And so we live in this interesting time in which we gladly know that we do not understand what is made 95% of our universe. That's why we call it dark. And that's why Calvin and Hobbes said that maybe this is a marketing problem, maybe astronomers, they have to find new names, new terminology for this kind of mysteries. So, why do we explore space? There isn't a wrong or right answer for this question. I just sum up some of the topics. Well, we need to satisfy our desire to explore. We know that since our first humans that made a lot of travelings across our globe. This is in our DNA. We travel, we explore for different kinds of reasons. Economics, for better living, so on, but we are explorers by nature. And also because it's inspirational. This video is from Cosmos, my favorite scene in Cosmos, when Carl Sagan goes to his primary school and delivers pictures, not slides in PowerPoint, real pictures to the students, and they feel amazed by touching the picture of a moon, of a planet. And that gives us the right to say that space exploration is indeed inspirational, and we see that in our youth. And then it encourages and appeals to the best of our species and often to our benefit. Yes, I'm talking about space spin-offs. And I'm going to address that later. And because we need raw materials from space. That's not a surprise for all of you. We know we have a very good idea of the value of some asteroids, and one of the next steps in the space exploration is explore the economical value of asteroids. And no, it's not an expensive investment, and the return is huge. Please take note of this point. It's not expensive. You know that saying about the American general that said in a war, what counts is location, location, location. Well, in space exploration and in space communication, in space education, what counts is perception, perception, perception. And we are in a fight against a negative perception about space exploration. I'm going to address that in the final talk that we are going to have. And because we need to explore space to survive. Let me tell you that the cosmos has magnificent ways of killing us whole. Magnificent. Let's start by asteroids. We know now probably 99, 100% of the orbit of the largest asteroids near Earth objects, but look at what we need to find out. Where are the 140 meters asteroids or the 25-meter asteroids? We only know 39% and 0.4% of those asteroids. That can affect a city, an hemisphere. So we have a long, long way to do about asteroids. And I put that picture over there to tell you another interesting ways that cosmos can knock our door. You know, in 2004, near Christmas time, there was a sudden arrival of extreme energy to our planet. What happened? In the other side of the center of our Milky Way, a very dense, a very magnetized star called the magnetar had a bad day, had stellar quake, and it produced an explosion that came across from that point, CGR, to our planet. Some of our space telescopes were malfunctioned because of that, and other satellites. And that happened very, very far away. And we also, I must remember you that we orbit a star, a sun, that also has its energy and energy output and solar cycle that we know, and that we can't right now prevent in a very fine way when we are going to have another solar storm. And finally, that last video, it's about a planet that it's always, always dynamic, transforming. It's not stationary. We can have volcanoes, we can have a lot of other events. We know that because it happened in other planets. We know that Venus and Mars were very, very similar to Earth in the past. But a lot of transformations, a little bit, the Sun has the blame also in one of the planets, but they had strong transformations that bring them today to the deserts that we know. So yes, we need to be a species that can go and thrive in other places. And let me just quickly say that we also live a very interesting times about how we see the universe. We are turning the page from a previous generation of space and terrestrial telescopes to the next generation of space and celestial telescopes that will bring us to new frontiers and new questions and new answers. These are just some examples of today's terrestrial telescopes that thankfully give me a lot of work for me every week to reveal about the cosmos: South African telescope, the Keck telescopes, Canarias telescope, the VLT and the ALMA from ESO, and the largest radio telescope in China. These are the telescopes that today still amaze us with its discoveries, but we want more. That's why we have the next generation space telescopes, like the Very Urban Observatory, 20 terabytes of data that must be processed and stored each night. The biggest camera that is going to be in a telescope. Or the extreme large telescopes in 2027 from ESO, 13 times more light than the large optical telescopes. Or the square kilometer array that will be able, imagine that, to detect an airport radar on a planet tens of light years away, in which Portugal is very well has an active role in this project. Or, obviously, our favorite, we are 1 week away of getting the first images of James Webb Space Telescope. Let me just give you a quick note about James Webb Telescope. The first truly revolutionary space telescope was obviously Hubble. Before Hubble, we knew that the universe was expanding. What Hubble told us was that accelerating its expansion. Before Hubble, we thought that universe, maybe it had 10 billion years. Hubble told us that no, it's a little bit older, 13.8 billion years. And we are just waiting for what James Webb will tell us about the very intimacy of the universe. And it will be in our lifetime. We will assist in the first row about the revelations that these telescopes will give us. I have an interesting video that one of the challenges that Ricardo told us about this conscience that we have right now about satellite industry. This is projection about how many satellites we are going to put in space for the next years. And let me tell you that a few weeks ago, it was published an article that said that in the next decade, most probably, we are going to have at least 4,300 satellites above the horizon every minute of the day and night. This is a problem for astronomy, for logical reasons. This is a problem for education. This is a problem for the ecosystems. Please don't take me wrong. I'm not against satellites. We are in an interesting crossroads because we need satellites for communications, for the Internet of Things, for rescue operations in our planet, but we have to do something about this problem. Because the other problem is obvious. The amount of pollution that we are creating in these nearby orbits of the Earth. This is a projection made by the European Space Agency, and we can see in different colors the debris size that are already polluting our planet. So, yes, as Ricardo said, and I agree with him, we are very good transforming this in a business. But maybe it's not enough. We have a lot of other challenges to address. This is a study made by the McKinsey company. They interviewed a lot of space leaders in the private and public sector, and these are some of the challenges that they say that will be the future preoccupations about space. Well, I'm not going to speak about Moon and Mars. Yes, this is also the epoch of space stations. We are going to see the rise of space stations for not only for tourism, but also for the pharmaceutical industry. And we already have the announcement of 3 space stations that are going to be deployed in the next years. Well, and maybe some others a little bit eccentric space entrepreneurship in space stations, just as Playboy once thought that they would get the first entertaining space station. So, the key to success, think big, always. We are in the month of the moon. 20th July 1969, when Armstrong and Buzz Aldrin for the first time touched the moon. And I bring you the video of what was discussed in CBS, the American television, just a few moments after Buzz Aldrin and Neil Armstrong touched the moon. Walter Cronkite, famous journalist, had near him a brilliant commentator, not like the one that you see Sundays morning in the Portuguese television, that's awful guy. But just a few moments after we touched the moon, that commentator, and was called Arthur C. Clarke, showed us the roadmap for the future of space exploration.
Arthur Clarke, one of my very favorite people, who has been with us at CBS for several of these missions now. And Arthur, what do you think we ought to do next? I mean, what would you like to see? The space station or Mars? Or Well, perhaps both. Well, I guess you'd like to see both. We all like to see all we can do, but given some national priority problems.
We will see both. I think the first order priority is the establishment of an economical space transporter so that we can establish a large space station which would act as an astronomical observatory, which will tell us a very great deal about Mars and the other planets before we get there, because then with large telescopes in space near the Earth, we'll learn a great deal about these places. And also, from the space station, in the space station, we can develop the techniques of long-range space exploration.
Arthur, you've been dreaming of this moment long before many of us did. Beginning back in the mid-1930s, you were writing about going out to the moon. What was your feeling when we saw this thing happen today?
Well, I don't think I did feel anything. I think we all sort of, time just stopped for me, and I think it stopped for everybody. It was just a hole in history, you know, and the whole world's, everything. My heart stopped, breathing stopped.
Mine certainly did, and I think all of ours did. I think you're absolutely right. I can't imagine a moment to equal this. The only thing I could imagine is if some fellow came forward and could say positively, we're not going to have any more war.
I think this is a step in that direction, because this sort of thing is making our stupidities here on Earth seem more and more intolerable. And I think this may be the greatest result of the space program.
Speaking of national rivalries, do you have any thoughts about what the Russians may be doing now that we know that their unmanned Luna 15 is in an orbit very similar to ours around the equator of the moon?
My theory is that it's going to land with a bottle of vodka.
A congratulatory bottle of vodka? Or a ceremonial bottle? Well, thank you, Arthur Clark.
Can you sense a little bit of similarity between those times and the one we live in? Just let me tell you that he is right. He was right. When the Americans touched the moon for the first time, the Soviet cosmonauts and KGB were all gathered in a building in Moscow. And when Armstrong touched the moon, they were celebrating with champagne. They said that they were feeling what they call it as white envy. Envy because they wanted to be them on the moon. White because, well, if it's not us, then I'm glad that humanity is there. And so we also must to get this feeling again, as space has arena for space cooperation, for peace, especially in these times. And I'm going to finish, yes, I'm going to finish now, okay? With a personal story. I don't do this. I usually don't do this. But I'm going to share with you 3 letters that I received in the television. And that's why you must work hard to inspire people. So, this was a letter from a gentleman that it's fulfilling his sentence in a Portuguese penitentiary. And he wrote to me, and he told me that practically the only moment that he has some liberty is when he's watching my show in the Portuguese television. He has some background in electricity engineering, and he sent me, in the first letter, he sent me the schematics of what he thinks. He thinks that it's the perfect propulsion system, better than the ones that are used by SpaceX. And he told me that I tried to send a letter to NASA. I tried to send a letter to ESA. I tried to send a letter to the Portuguese Space Agency, but they never answered to me. But I have the solution. I'm not an engineer, and I'm going to help him. But the most touching lines of that letter was that I used to think about space to escape from the prison. Thank you.
I invite you to sit here. Thank you very much for your presentation, quite inspired presentation. We know that you are prepared something special. And let me see if I can follow this now. So we will jump for our next guests, and they came from the University of Aveiro. She's Slavka Carvalho. She's a principal investigator at the Portuguese University and special expert collaborator for the SAM team at NASA Goddard Space Flight Center. And from 2016 to 2019, Slavka was a researcher at the Mars Curiosity rover mission. And today she will give us a talk about NH4 smectitis, part of the nitrogen cycle on Mars. So I think the floor is yours. I have here also, and then you will invite Ricardo also to join the stage, right? It is in the next step, right? Okay. Stage yours. Thank you very much.
So first of all, I would like to thank the organizers for having me here, and it's my pleasure to share with you an exciting science the Curiosity rover does on Mars. Okay, let me see if it works. All right. So follow the nitrogen has been proposed as a strategy in the search for both extant and extinct life on Mars. Nitrogen is so crucial to the life on Earth that life developed metabolic pathways to break the triple bond of the nitrogen molecule and fix atmospheric nitrogen to more biologically available molecules. Nitrogen is also a bioessential element. It's a component of all amino acids and nucleic acids. They make proteins, DNA, and RNA. So nitrogen is actually a key to life. So on Earth, we have a nitrogen cycle in which nitrogen fixation is predominantly biological, and it occurs by conversion of by atmospheric nitrogen to ammonium and nitrates with the help of microorganisms. We have also a biotic nitrogen fixation, which is happening by lightning and volcanism, but it occurs at much lower levels. But the question is, was there a nitrogen cycle on Mars? In 2003, Mancinelli and Banin, these two authors, published an article with the title, "Where is the nitrogen on Mars?" At these times, we knew that there is nitrogen only in the atmosphere. And these authors also suggest that a focused search for the traces of nitrates and ammonia in the Martian soil during the future missions to Mars will provide important information regarding the nitrogen abundance on Mars and the potential for the evolution of life on its surface. So accessing nitrogen availability is a key part of the Curiosity rover's mission to characterize Martian habitability. So a few words about the Curiosity rover. The rover landed on Mars almost 10 years ago in the Gale crater. Its main scientific goals are to study habitability, to search for an environment favorable for past or present life, and to search for nitrogen. So to accomplish these scientific goals, the rover is traversing this Mount Sharp mountain and is analyzing different geological units. And while it is traversing, It drills the samples, which are later analyzed. So Curiosity rover has two very important instruments to analyze soil samples. One is called SAM, Sample Analysis at Mars. This instrument is in the middle of the Curiosity rover belly, and it was specifically designed to measure volatiles from the Martian soil samples. This instrument is the most complex instrument ever sent to the Martian surface. That's okay, it's cut it. So how it works is that the soil sample is in this instrument heated to the 900 degrees, and the outcome are masses of evolved gases. The other instrument is a CHEMIN instrument. It is chemistry and mineralogy instrument. It's just power X-ray diffraction instrument which analyzes crystalline and amorphous phases in the Martian samples. All right. So SAM is one amazing instrument because in 2015, it actually detected nitrates in the soil samples on Mars. And how actually the SAM detects nitrates? So as I told in the previous slide, SAM detects masses of the evolved gases. And when you heat nitrates, one of the evolved gases is NO, or nitric oxide, or mass 30. So that means that all these Martian samples contain in their pyrograms NO. The abundance of the nitrates in the Martian samples is quite low. The maximum value is around 680 ppm. And so for this reason, nitrates have not been identified by CHEMIN instrument because their content is below the detection limit of the CHEMIN XAD instrument. All right, so we have nitrates, but what about ammonia or ammonium? So reduced nitrogen could have been at one point present on Mars due to nitrate reduction by iron or even biological fixation. We know that ammonia is volatile, has short atmospheric lifetime, but ammonium can substitute cations like potassium, calcium, sodium in the interlayer space of smectites, and this is the process really common on Earth. And then we have also good news because clay minerals are abundant on Mars. As I thought, these are really good news, but in Martian samples is usually present one mineral or chemical which is called perchlorates. And when they are heated, they evolve oxygen. So what it means? So if we have in our soil sample ammonium or ammonia, this oxygen during the heating oxidizes ammonium and ammonia to NO, or nitric oxide. So the question actually here is it possible that some NO detected by some in clay minerals are oxidized ammonium cations by perchlorates? So to understand this process, I am the one who needs to prepare ammoniated samples. Then we characterize them, analyze them, and we compare our data with the data from the Curiosity rover. So the clays minerals or smectites which I usually work with are montmorillonite and nontronite. These clay minerals are standard clays which are used by many clay mineralogists in the world, and they are very well characterized, and we believe that they are also present on Mars. The only difference between these two, well, there is more differences, but the main important difference is that montmorillonite is aluminium rich and nontronite is iron rich. And actually, nontronite is based on the color more Mars-like because it is more brownish compared to the montmorillonite. So my goal in the laboratory seems simple, but this procedure takes several weeks. So I need to exchange these interlayer cations, which are in the natural samples, calcium, sodium, potassium, by ammonium cations. Here is a written procedure, but I'm not going to talk about it now. So, and then these prepared samples, as I mentioned, we analyze by Chemin-like and SAM-like instruments. I'm saying Chemin-like and SAM-like because at NASA Goddard we have copies or replicas of these instruments which run in the same experimental setups as the instruments on the Curiosity rover. All right, so in this figure are XRD patterns of my ammoniated samples and Martian sample marimba. On Earth, it is really easy to distinguish smectites based on this characteristic peak. And the position of this peak depends on the interlayer cation which we have in the interlayer space. But of course, on Mars, everything is dry. So it means that clays are collapsed, they are dehydrated. Because in that interlayer space, besides interlayer cations, we have also molecules of water. So everything again on Mars gives us number 10. So I had to perform some laboratory experiments to simulate Martian conditions, and what I could reach was that ammoniated nontronite gave a value 10.4 angstroms, and ammoniated smectite or montmorillonite gave us 10.8 angstroms. So as you can see, these peaks are not really in the same position, but if you see more closely the peak of marimba, it is kind of broad, and it has this bit of tail where actually ammoniated nontronite and even ammoniated montmorillonite could be hidden. So then I performed SAM-like EGA analysis. And in this case, I added to the samples magnesium perchloride because we wanted to see if really ammonium cation will oxidize to several nitrogen oxides. So what happened is that we got this green line, which is actually evolution of nitric oxide. So as I mentioned, when we heated the samples, ammoniated clays, we really noticed that ammonium cations oxidize to the NO in both cases. This is ammoniated montmorillonite, and here is ammoniated nontronite. And the best thing was when we compared our data with the data from Mars. So in the case of ammoniated Wyoming montmorillonite, we see that NO evolution between 550 and 580 C is consistent with NO evolution in the Martian samples Coela. When we compared our data from ammoniated nontronite with some Martian samples, we see again that evolution of NO between 200 and 600 C is consistent with Mojave and Confident Hills. So, was there a nitrogen cycle on Mars? So while NO evolution from Martian samples analyzed this sum is consistent with the thermal decomposition of the nitrates, the NO from oxidation of ammoniated smectites is also consistent with NO evolution from several Martian samples. Chemin-like XRD data from ammoniated smectites is also consistent with some chemic analysis on Mars. So, if ammoniated smectites are present on Mars, this could confirm a potential primitive nitrogen cycle on the surface of ancient Mars, and then it is very important to consider it when assessing Martian habitability. Oh, and ammoniated smectites have also been identified from orbital observations in the dwarf planet Ceres. And future missions to Ceres may also have thermal analysis instruments, and if so, our analog studies could help in the interpretation of the data from analysis of Ceres samples. Well, thank you very much for your attention.
So I will invite Ricardo Oliveira to come to the stage. Please, Ricardo. Ricardo is a master finalist in geological engineering, and He will tell us about one of his current research interests, cabeço de vide serpentines and their implications for Mars. I'm curious to hear about it. So, take the stage and start the presentation, please.
First of all, thank you so much, and thank you to Anna and everyone involved for inviting me to talk. So, I'm here to present to you a short introduction and some preliminary results about my thesis on the cabeço de vida serpentines and their implications for Mars, where I'm supervised by Professor Slavka Carvalho. So, first of all, nowadays, serpentinization processes are considered possibly the most relevant process, are possibly the most relevant metamorphic reactions to explain the origin of life. Its research efforts can be dated back to 1995 and 2001, when the existence of planets outside the solar system and low hydrothermal fields were first discovered. So then, coupled with the knowledge that the undifferentiated crust of terrestrial planets like the early such as Mars and the early Earth is largely composed of ultramafic and mafic rocks and minerals, these observations have led to an increased interest in the origin of life, both terrestrial and extraterrestrial. So clearly, we can say that understanding serpentinization processes of ultramafic rocks is one of the main pillars in linking life sciences with solid earth processes. So you may ask, what are serpentines? Serpentines structurally are phyllosilicates with a general formula showed there, and they form during hydrothermal alteration of ultramafic rocks at temperature ranging from slightly ambient to 400 degrees Celsius, following this interaction. So basically, serpentinization occurs in the presence of liquid water and carbon dioxide fluids, resulting in the production of significant quantities of hydrogen, methane, and lesser quantities of long-chain hydrocarbons. So hydrogen, this has a lot of interest in relating serpentinization with life, because hydrogen can be utilized by microorganisms to gain metabolic energy, and methane can be formed either through reactions between molecular hydrogen and oxidized carbon, or through biotic processes. So on Mars, we have a little scientific experiment that is super important, that's called Perseverance rover, that landed in Jezero crater on Mars in February 18, 2020. And Perseverance rover is analyzing the environment where serpentinization processes occurred, with the main objectives of studying the rocks and landscape at the landing site to reveal the region's history, also to study the area to understand its historical climate and environment, as well to study its geological diversity, and finally to study Mars habitability, seeking past signs of past microbial life, collecting samples, and preparing for future human missions. So taking in consideration all this information, we can surely state that knowing and analyzing the detailed mineralogy of terrestrial Mars analog samples is essential to analyze the data acquired by rovers on Mars. Mars analogs are environments on Earth, providing similar geological formations and mineralogy as those on Mars. So the study area of my master's thesis is called Cabeço de Vida. It's a little city located in the Fronteira municipality and in Porto Alegre district, in the northeastern part of Alentejo region in mainland Portugal. So, active serpentinization represents a widespread geological process that has been described from a number of deep-sea sites, like a location near the mid-Atlantic ridge called Lost City. However, serpentinites and related serpentine soils comprise less than 1% of the Earth's total exposed surface and are commonly found in ophiolite belts along tectonic plate margins. So in recent times, a wide body of research has demonstrated the importance of active continental serpentinization driven by meteoric water, occurring in peridotites already in place on the continents, in ophiolites, peridotites massives, or intrusions. Cabeço de Vida, with an active continental serpentinization process driven by meteoric water in mafic and ultramafic rock intrusions, provides an excellent opportunity for the investigation of continental serpentinized rocks on Earth, with the emphasis that the majority of the published papers are focused on serpentinization in ophiolites. So spectral orbital data from Jezero crater has identified a wide diversity of minerals, including olivines, pyroxenes that are ultramafic minerals that we talked before, feldspars, serpentines, smectites, and carbonates. And all these minerals are also present in Cabeça de Vida, what points to a similar geological processes leading to serpentinization in both locations. So the fundamental objectives of my thesis include the detailed petrography of the Cabeça de Vida ultramafic rocks in what concerns both textural, mineralogical, and crystallochemical features, allowing us to put forward a genetic model for the serpentinization processes. Also, the study of the associated mafic rocks and the surrounding carbonate rocks that host the Cabeça de Vida ultramafic massive, as well as the biosignature preservation, including the presence of amino acids, the DNA sequencing in clay minerals of my study of the study area. So, to achieve established objectives in terms of biosignature preservation, and with the incredible help of our two biology scientists who are here today, we first started with what we like to call serpentine powder. Then we did the DNA extraction using the DNA purification kit by Invitrogen, followed by PCR, which through electrophoresis, we managed to get this amazing image. It might not seem amazing, but it's amazing because this image basically confirms that we have DNA in our serpentine samples. So this is where we are today, and the next step is to sequence this DNA for bacteria and archaea domains, which are the most representative domains for microbial life. And then, through bioinformatic analysis, we will be able to do the interpretation of this biological data. So, as I mentioned before, bacteria and archaea are the most representative domains for microbial life, and they are capable of adapting and surviving in extreme conditions, like temperature, salinity, and nutrient scarcity. So they have simple shapes and a metabolism diversity, since they can have multiple sources of energy, like hydrogen, carbon, and sulfur. And for example, methanogens, they use hydrogen as a source of energy, and they release methane, which is really important. So basically, and to finish, if we in fact manage to identify these groups of microbial life in our samples, we can consider then serpentines are a great starting point in the search of life on Mars. And we can surely state that this will have immense implications for the Perseverance Mars mission and possible formation of life on Mars. Thank you.
Thank you, Ricardo. Please join us. I don't know if you know, but I was raised in the United States, where there's a very healthy true crime television culture, and I'm one of the fans. And it reminds me when I see this that you have, and I have a deep appreciation for you uncovering the mysteries and the history of planets, because it's just as fascinating to trace where we come from and how to understand other planets. So thank you very much for the work you're doing. And thank you, Slavka, as well. It was very fascinating. So we are now going to have a video from another guest. Yasmina Martin has a message for us from NASA Goddard Space Flight Center.
Hello, everybody. I'm Yasmina Martos, and I work at NASA Goddard Space Flight Center as an assistant research scientist. I basically mainly work on magnetic fields, magnetometers on Earth, and also studying other planets. On Earth, I work on magnetometers and magnetic fields to understand what lies beneath the surface, and for example in Antarctica, to understand what lies beneath the ice, that ice sheet of 4 kilometers. Studying those places, remote locations on Earth, help us to, for example, improve techniques, an instrument that we can send to other planets, to somehow have it as terrestrial analogs that will help astronauts in the future to find, for example, caves beneath the surface and the moon on Mars, and then be safe from radiation. I also work in the outer solar system, and for the Juno mission, I work for the magnetometer team, understanding the the Jupiter's magnetic field and the interaction with the moons like Io and Ganymede. I'm very excited what it's coming in the future with the new exploration for the outer solar system and also with the returning of the humans in the moons and hopefully stepping foot on Mars. So I'm very excited to see all of that. So hopefully you have a very good time on the workshop. I wish you a wonderful time there, wonderful discussions to improve the future of space exploration and humankind. Thank you.
Wonderful. And now it's my pleasure to introduce our next speaker. It is Dr. Rui Moura. He's a professor at the Faculty of Sciences of the University of Porto and a researcher at INESTEC, Center for Robotics and Autonomous Systems. He has more than 25 years of geophysical exploration fieldwork and experience performing scientific measurements in harsh, wild environments. The role of planetary geology, from short microgravity opportunities to lunar science exploration. So I hand it over to you, Rui.
Thank you, Yvette. Firstly, let me thank the organization, Anna, which is a force of nature, as I usually call her, UT Austin ISEP for inviting me. And also I'd like to say that it's my huge pleasure to have, after 6 years of participating in POSSUM and International Institute of Astronautical Sciences, have my friends, colleagues, and mentors here. Aaron, Jason, Yvette, and all of you come, and of course Mark, who's almost part of the team as well. And it's a great pleasure to bring a representation of the experience and learning curve that I've been able to gain through being involved. So without further ado, I'm going to talk about the role of planetary geology in terms of how it can be considered an important science field in space exploration. So I'll just start with this first image. And this is Harrison Schmitt in front of Boulder in the Taurus Littrow field, where they went on the last mission, the sixth mission to the moon, and he's there doing normal geological chore, which is taking samples. So it's an inspiring image, and you can actually see there the lunar rover park. It's an amazing image to think about. So planetary geology and how did it start? Well, one of the great pioneers of planetary geology was this gentleman here, Eugene Shoemaker. Eugene Shoemaker wanted to be an astronaut, but he couldn't get to be an astronaut. He had some health issues. I think he managed to apply. He's here in this sort of a space cowboy suit, but he was never an astronaut. But he had an important role. He had to test what he, as a geologist, knew were important physical demands of sampling in the field. So he had to try for himself what it would be like to do geological tasks in the field. So, things like bending down, and, rapidly they understood that this was not a good idea. So they had to develop tools, of which you will see some of them in the next few slides. The curiosity, you probably remember, or some of you more in touch with astronomy, the Shoemaker-Levy comet that collided with Jupiter back in 1994. Well, the Shoemaker part of the name is in a tribute to him. I was there actually with Yvette and a couple of others who endured on the last day. We visited the United States Geological Survey Astrogeology Center in Flagstaff, Arizona, after a course that I took with the International Institute of Astronautical Sciences in EVA procedures in geology. And we visited the place where astronauts were trained and actually where most of the data was analyzed in terms of the moon, Mars, Mariner missions, all of the missions you can imagine that need some kind of geological analysis. They are centered here. So as you can read on this plaque, which is in the hall, every astronaut who walked on the moon trained in Flagstaff. So this is the importance of this place. So going back to the Apollo era and the importance of geology, I would say that we had to train pilots to be geologists. And you can see here the last crew. This is Harrison Schmitt, the only scientist to ever have walked on the moon. And he was a geologist. He actually worked at the Flagstaff Center of Astrogeology. Ron Evans and Eugene Cernan. And this is my favorite astronaut of all, John Young, a super astronaut, the astronaut of astronauts, in my opinion, here doing what geologists do, taking samples, looking at rocks, and smoking a pipe, which you would never think an astronaut would. So, but at the same time, geologists had to be pilots. And this is Harrison Schmitt learning to fly an airplane. And some people might think, well, why does a geologist have to suddenly learn to fly an airplane? And the way I see it, it's a little bit, I have piloting experience, and the way I see it is when you have to manage systems and understand subsystems, and you have to do them in a timely, calm, and collected manner, the best way to go to the gym to train your senses is actually to fly an airplane, actually a high-performance airplane like this. So this is one of the reasons why it's typical for astronauts to undertake pilot training. So he had to learn to fly an airplane. They also had to do analog missions. This is the rover that they use to simulate their EVAs. It's a little bit like going to the theater. You don't want anything to go wrong on the last day, so you rehearse and rehearse because you have a limited time to do your geological tasks on the moon, so everything must be done to time, and you have to test if you can do them in the time frame that you have. And you also have to do sampling. So rock sampling is an important thing to do. And this is Harrison Schmitt again with Eugene Cernan rehearsing what they have to do, and with all of the, the obstacles of carrying a backpack and the communications, and they had to rehearse if they had time to do all these things. And it was done in this place. And if you notice here, this is SP crater, which is this here. So it's exactly the same place, although that's me not taking notes on a computer. The other thing is doing rock core sampling, and this is an instrument developed for rock coring on the lunar surface in the Apollo days, and so they were testing how you could do it. Because one thing is doing this with your clothes, another thing is doing it in a spacesuit. It's completely different. So we've had the experience and benefit of having tried to do simple things like switch buttons and manage a camera. It's completely different under a pressurized spacesuit. It's not the same thing. So when you want to go to the moon and you want to do these apparently simple things of drilling a rock core, you must train with a spacesuit. This is my colleague from the university doing a rock core for magnetic analysis of the rock core, Elena Santovaya. She's director also of my institute. This is another thing you need to do, to carry out observation. This is a crater field created artificially in Flagstaff, Arizona. This is in 1972, I think, 1972. You can possibly see this hill here, that same hill, and that's me. During the same EVA 103 course we did in Flagstaff, Arizona. This place was actually created by explosion, so it was artificially created. The same crater layout they had on a specific place in the Sea of Tranquility. So this is the Sea of Tranquility taken by, I think, the Ranger or the Lunar Ranger missions, and this is a crater field created in Flagstaff, Arizona. This is us. We also, coming to the issue of craters, the recognition and the observation power of, doing a geological field, a lot of it is observation. So if you want to refine your senses and fine-tune your senses to how you should describe and pick samples, one of the things is going to a crater. This is the largest, best preserved crater we have on Earth. Well, it's actually not the largest, but it's the largest, best preserved crater we have on Earth. It's also in Arizona. It's a half an hour away from the astrogeological lab. And this is back in the Apollo days. These are astronauts with Eugene Shoemaker. This is us. Where is Anna? Anna is there. I'm there. Jason is there. Aaron and Yvette there. Nice smiles, and that's us. And this is the current future astronauts that will probably walk in the moon in a couple of years. So we've had the benefit of having this experience, and this is the way to go. You do a lot of field work and train to be a good observer. This is Neil Armstrong and Buzz Aldrin. We're in the week of pre-moon anniversary, and this is Rui Frutuoso, sorry. He is one of my students from the Faculty of Sciences, and this is Victor Glover. So observation is something done, and it's common to any kind of geological exploration path. Tools. This is Jim Lovell, Fred Hayes, Pete Conrad, and Alan Bean. Training with tools. Tools is an essential part of doing things in terms of geology on our planet, and you need to design new tools that can work in such environments. We had the experience of doing that too. This is Shona Pandia, who's actually at GLEX, or was at GLEX recently in the Azores. She was a friend, colleague, and she developed a sampling tool. Aaron there with his tool, developed for specific EVA tasks. Anna also presenting and demonstrating how her tool works, and Shaila over there. So these are sampling tools, examples of sampling tools that we use in these things. And we come now to my specialty in geology. So I'm a geophysicist, and this is an example of banging or creating a shock wave, an artificial seismic wave, so that you can make a cross-section through the Earth and understand what the composition, the physical composition of the subsoil looks like. And this was done also during the Apollo days. They did geophysics on the moon, and they trained on Earth to do it. This is an example of the profile they created and that they collected on the moon. I think this is Jim Irwin, I think. And no, sorry, he's not Jim Irwin. It's Charlie Walker. Charlie Duke. And this is me, roadside somewhere here in the north of Portugal, doing the same thing. They also deployed seismometers. This is some images from the Apollo days. Seismometers were fundamental to understand the composition and the structure of the inner moon. And this is a magnetometer. We talked about magnetometers recently. This is the training they did on Earth. So you need to rehearse, as I said, so that anything in terms of the deployment of the instrument on the day that you get to the moon gets correctly deployed. Curiously, Charlie Duke set up his magnetometer on the moon, and he tripped over this wire, and he ruined the instrument. So that was a blunder. So you train and train and train, and then even sometimes things go massively wrong. They also did gravimetric studies with a gravimeter, and as you can see, this is the training on Earth and the actual moon deployment. So what did we learn from all of this? Well, we learned many things. But one of the things was the structure of the moon. We learned an interesting thing, that the side that faces us has a thinner crust than the far side. And what we can see is the moon also has a very faint seismic activity. It doesn't have a lot of moonquakes, but it does have some. The other thing we learned was the age of the moon. And for that, on the later missions, namely Apollo 15, they were searching for these white rocks, which could possibly be remnants of the primitive crust of the moon. The primitive crust of the moon was formed by the minerals that solidified first. And these minerals that solidified first, from what we know on the geology on Earth, have this whitish aspect. It's a plagioclase, and it's an anorthite. And when they were on the moon, since the pilots, most of the astronauts that went were test pilots, they had to be trained, as I said, in geology, and they had to refine what we call in Portuguese our olhometer, our iometer, to detect and to distinguish which these rocks would potentially bring back older ages. And this is the transcript of the dialogue between Dave Scott and Jim Irwin, and he says, "Oh man, look at that," and things like that. So they were really engaged. They were enthusiastic about carrying out geology on the moon. So what did we learn? Well, we learned that the moon could be up to 4.51 giga, or how we translate this into 4,510 million years of age, which gave us not just the age of the moon, but also the age of the Earth. the composition, the average composition of the moon is also very similar. So what we think today is that actually the moon and the Earth resulted from a collision from a proto-Earth and a Mars-sized planet called Theia. So we learned a lot by going to the moon. We learned where we came from. We're going back in the future, not very far future, the very near future. This is an aspect of the mission that will be done on the moon with the lunar base. And from these 18 people, which you can see have different backgrounds in terms of their training and their background, their academic background, maybe one of these 18 people you will see on the news when they step, and namely the first woman to step on the moon. At the moment on the International Space Station is a geologist. And you have here another geologist, but you have many engineers, biologists, doctors, and this is the beauty of doing science in space. Space is not just for pilots as it was in the beginning, now it's for all professions, as you can see here. So, in terms of some of our research that we've carried out research in terms of seismic. Through the things that I've done and the experience that I've gained through the International Institute of Astronautical Sciences. This paper, conference paper, was published a few years ago. I reprocessed the Apollo data, the seismic data, and I got a new cross-section. This is a slice into the Earth. So this is the surface, and this is a cross-section. Where you get the cold colors, it's soft rocks. Where you get the dark, where you get the hotter colors, it's hard rock. So there is like a buried underneath the soft soil. You have here sort of an outcrop. Well, it's not an outcrop. It could be an outcrop, but you have here sort of a bedrock. So this is the interpretation from the 1960s. And this is obviously very different from what I got, much more detailed. And some other research into microgravity research into seismic properties was done on one of the parabolas that I did back in 2018, I gather. So this is the general view of a parabola, and this is the general profile of carrying out the parabola. And during those parabolas, I floated this seismic experiment along with some others. Namely, by the way, this aircraft is also used by the Canadian Space Agency. These were some of the results. And Anna also had the opportunity to carry out her research in microgravity. And this also resulted in a paper. And as you can see, her experiment was about a hardness test, which you can see in the next slide. So this is Anna doing her hardness testing during one of the parabolas. We'll just see in a moment how it looks from a microgravity perspective. So you see there Heidi, I'm not sure who's in the flight suit. But this is some of the research that Anna has carried out in terms of the properties of hardness from a pundit type instrument. So another interesting aspect of the research we've carried out was in terms of this LIBS analyzer, which can be carried to the field, and you can do this type of measurements in planetary geology. We did similar studies with our training, although this was not a LIBS, this was a spectrometer. Shortly, in the next month, I have the pleasure of announcing, I hope it will be this year, we will have a payload on the next flight of Blue Origin rocket. So it will be flown in a suborbital flight from Texas, and we have an experiment that was partly developed also here in ESTEC, and it will hopefully be flying in July, in August, and in July we will be preparing and we'll hopefully show you some results next time. This is the rocket and the capsule, and I hope this experiment will result in something. And in terms of other studies we've carried out, we've been engaged in regolith studies, and this is also a presentation we presented a few months ago, based on the geophysical properties of regolith. So, thank you. This is just a short overview of the type of research that can be done and the role of geosciences that can be done in terms of space, and namely that can be done in microgravity. Thank you.
Thank you, Rui. I invite you to sit here. And now this is a moment. Have your seat here, please. And we have a moment for the Q&A. We received the precise instructions that you have 5 minutes. I don't know if we still have 5 minutes, but I want to open the floor to you and someone that raise your hand if you want to make a question to our panelists here, including ourselves. So, volunteers.
It's a question for everyone. Just your quick insight. What we heard from you here today is how important is Earth to study and to test and to develop a lot of, for example, serpentines, clays. How important is Earth to test and to demonstrate and to help us to go to deep space and to go and to develop tools for space exploration. I would like to know your thoughts, your insights.
Rui, I think this is directed to you, this question. Then we can ask if someone there have some position.
As I was saying, so the things we do in terms of geoscience research tells us a lot about the possibility of discovering ourselves. We went to the moon to discover ourselves. We knew our age. We didn't know our age before we went to the moon. We were not sure. The moon is a frozen planet in time, or planetary body, as more precisely. The Earth is a very dynamic place. It has erosion. It has plate tectonics. So all of the evidences of our origins are not DNA, but the past evidences of what we were in the beginning have vanished, and we needed to go to the moon to discover ourselves in terms of origin, in terms of age. So we also discovered the possibilities into the origin of the solar system. So, in essence, geosciences is a way to discover where we came from. Michael Collins said in a public talk once a very interesting phrase. He said, it was based on something his father, a military man, told him. His father used to say, if you want to bring the riches of the Indias, you must bring with yourself the riches of the Indias. So how did he connect this to the space exploration? Well, he said, well, we spent a ton of money developing all this technology, the brightest minds in the US, and we brought our vehicles, our instruments to the moon, and we brought back rocks. So that was the riches of the Indias that they brought back, and that was a very important thing, because with those rocks, simple rocks, which we all take for granted, we discovered ourselves. So that is the main importance of geoscience, in my view, is not just the rocks and the analysis and the serpentines, but also discovering things we care about. Life, where did life start? Our curiosity. Going back to the talk also that Miguel said, the curiosity of children in a room with and enthusiastic of looking at the images of planets with Carl Sagan, and so basically that's it. That would be my take.
1, 2, 3, 5, 6. I will ask for other questions if you have some. Oh, there are questions there. Please tell your name and what you are doing here.
Teste. Ok, está a funcionar. My name is Gustavo. I've simply come here to have a perspective of all the kind of technologies and endeavors that are currently being explored. And I'm particularly interested also in the more biological aspect. But there's one thing that I really wanted to clear that I've never really heard being properly addressed. So I'm just going to address the elephant in the room, or shall I say, the cloud of debris that is currently orbiting on Earth. So the question is, what is the most promising technology that could be used to clean this debris? And the second question is, where is it going to be kept, thrown? Are we going to do it like in the Futurama, where they threw it to the sun, or are we going to keep it on Earth? Are we going to throw it outside? There's a lot of possibilities. I'm sure someone has already thought about this.
Part of your question I can answer that can give you an answer. One thing that we need for sure is international collaborations and to implement some practices and some standards. And this is linked with the efforts that we are doing today in the international arena, in particular in the UN, to try to see if we can get some kind of frame program and with some to implement some standards and also some technologies how to launch satellites, how to include some measures to remove the satellites from the orbit and to mitigate the problems of the space debris. This is a huge problem. There are what we call the monitoring itself, the space debris, but there are another, let's say, dimension which is removal. And removal, particularly the space debris and satellites and many other objects that surround the Earth that are not anymore operational. And there are some already some, and Portugal participates some programs and some to prove the technology to do it. And there are so many dimensions that we can explore. There are several configurations to remove, to launch rockets, to like a Pac-Man in space. You remember, you saw this Pac-Man. But one of the main problems that we have, and this is more difficult than the rocket science, is to try to put all the actors to collaborate. This is really difficult because you can have a frame for collaboration, but for example, probably you know that 1 year ago, I remember, I think it was 1 year ago, that one country, Russia, did an anti-satellite testing, right? And this is totally against the spirit to collaborate, to not spread debris. This is the difficult part. We are at the European level try to engage all the stakeholders, companies, agencies, to have some kind of harmonization in our space laws to implement some measures to avoid this problem. But this, we are talking to the future, right? But there are some good news also. One of the things is what we are preparing, some other programs, is the spirit of in-orbit servicing. It will have some, look, for example, we are exploring now the opportunity to have commercial space stations, right? And one of the dimensions of these commercial space stations is to act in orbit servicing. There are probably some companies, their job will to remove and to re-entry and to try to implement some measures to mitigate this problem. I don't know if you want also to have some thoughts on that. Miguel, you want to say something? Rui?
Just to address, I was still thinking about Anna's question about Earth. I'm just going to do the reverse exercise about how moons and other planets in solar system can teach us about our own planet. For instance, there are studies about the evolution of the weather in Titan, a moon of Saturn. Titan is probably the only moon so far that has a very dense atmosphere, denser than our own atmosphere. And it is considered very similar to the atmosphere that the ancient Earth had. And so right now there are scientists that look at Titan as a time machine and to understand how the evolution of that ancient atmosphere was similar to our own. Or, as I said in my presentation, how the evolution of both Venus and Mars can teach us about our own planet, or for instance, Mars. We know that the importance of the moon to stabilize the axis of rotation of our own planet. That's marvelous to have the summer, the session that we have, the weather that we have. But Mars never had the chance to have a big moon like we have. And so Mars never had the opportunity to stabilize its axis of rotation. But it's important in a planet like Mars, the orbit around the Sun. It's much more eccentric than the planet Earth, our own planets. So we study our other planets and other moons as time machines also to understand our own planet.
Yeah, just quickly. The space debris is, of course, a big problem. There is a challenge to orbit with a dead satellite and collect it and bring it back or do whatever you want with it. The alarming thing about when we see the images of space debris, and you can go to a site which is called Stuff in Space, I think, you always have to reflect on those images because although I'm not diminishing the problem, but some of those objects that you see orbiting are very small. We have a capacity with radar to detect objects of around 10 centimeters. And if you see the scale of the image, the depiction, some of that is exaggerated. If you do the math, some of those objects would be kilometers in size. So the problem is a problem. It's a technical problem, but it's not as dramatic as you see. For an operator of a satellite, it's a big problem. For the operator of a space station, it's a huge problem because you have humans there. But it is frightening, but not as frightening as the image, I would say. So it's good sometimes to put the things into perspective, I would say. And there is a large volume of those debris that are not even in places where you would want to orbit. They are probably further near the Van Allen belt, so you would never go there. But for satellite operation, it's a problem. I think it's a headache for anyone who wants to operate satellites, but I wouldn't say it's an environmental problem, though sometimes it's depicted as an environmental problem. That's something which I think is wrong.
At the end, really, it is our footprint also in the outer space, right?
Yeah.
Okay, we need to conclude here. Final notes.
Just to remind the irony that it was a space picture that started the largest environmental organizations in our planet. The Earthshine picture of Apollo 18 was considered one of the most iconic pictures ever taken in this space age. And so now we are in this very fine irony of addressing our own problem of pollution in space. It's just a reminder of the irony.
Thank you, Miguel. And also, let me tell you that in this perspective of in-orbit servicing, there are some kind of migrations for not observing space debris from the ground, but observing space debris from the space. So what I, in my introduction, as you just mentioned, space-to-space business.
Hello, Portugal, from the top of Boulder, Colorado. I'm on this peak called Bear Peak. It's a training peak that I use regularly because I'm a mountaineer as well as being a scientist and science educator. So I started this citizen science initiative called Science in the Wild, getting people outdoors, interested in science. And as far as the space side of that, that's been in the Atacama Desert of Chile. It's the same places where the NASA rovers practice for Mars. We've gone there to understand the landscapes. I've been to the interior of Iceland in the footsteps of the Apollo astronauts where they did their training. And then with Project Possum, I've been co-teaching a planetary field geology class, also where the Apollo astronauts did their training. So I'm really excited for the future of space. Commercial space is opening up. I mean, just like Mount Everest, that we saw that shift where more and more everyday people can go up. I see the same thing happening for space. I see potential university degrees being granted for space exploration, development, perhaps a lunar base. So it's really an exciting time to be alive and see where things are going to go. In Portugal, I salute you as an emerging space nation. I celebrate your achievements thus far, and I wish you the best of luck in your workshop and beyond.
Hello everyone, my name is Stephen A. Dare. I'm a Johns Hopkins Systems Engineering graduate student, Confer's Consortium Communication Working Group co-chair, Citizens for Space Exploration volunteer, and CEO of Protean Industries. My university research focuses on human-machine systems engineering to develop geospatial robotic systems for planetary exploration and in-space servicing, assembly, and manufacturing. I am a contributor to the Lunar Surface Science Workshop and the Interstellar Probe flagship mission with NASA. The Protean Industries team and I are developing geospatial robotics focusing on Earth, ocean, and cave exploration, aiming to provide baselines for human-machine operations, planetary explorations, and ISAM. My work with the Consortium for Execution and Rendezvous and Servicing Operations, CONFERS, aims to leverage best practices from international governments and industry to lobby, research, develop, and publish non-binding, consensus-driven, technical and operational standards. The standards and systems we are designing with our teams are providing the foundation for a new commercial repertoire of robust space-based capabilities and the future space economy. These capabilities relate to manufacturing, refueling, repairing, recycling, upgrading, and accessing in-space natural resources. This translates to building the ISAM infrastructure, providing the gas stations, grocery stores, hotels, mechanics, and spaceports needed for a thriving space economy that reciprocates to industrial growth on Earth. I meet with and brief international leaders across industries and governments, developing engineering diagrams, coding machine learning models, and conducting research in oceans, caves, jungles, mountains, and laboratories to improve the simulation baselines for exploration, space operations, and ISAM. Portugal was one of the primary actors in the European age of exploration and discovery. Prince Henry the Navigator laid out the groundwork for modern globalization. Portugal has a unique position to continue extending that heritage into our solar system and beyond. The current and future space ecosystem and economy require numerous actors and activities on Earth and in orbit to promote mission safety and success, including universities, ground stations, teleoperated robotic flight providers, production plants, spaceports, and training facilities. These efforts must be international and intentional to persistently promote the peaceful use and exploration by humankind of outer space as we transition into spacekind. Thank you for the opportunity to participate in this conference, and I look forward to visiting your beautiful country and university next year. Live long and prosper.
Now it's time to talk about space medicine, microgravity research, and astronautic science. And for that, we have invited the three top-notch speakers. To start, let me call to the stage Jason. Please come to the stage. Jason Raymuller is the Executive Director of the International Institute for Astronautics Science and the project POSSUM Research and Education Program. So today Jason will give us, I'm reading because then I will become lost. Today Jason will give us the chance to walk through the IIAS research facilities, right, Jason? And to learn about the Institute's educational offering. So, this is yours.
Thank you, Ricardo, for the introduction and the invitation, and everyone that has worked so hard to make this possible, especially Anna. It's an honor and a privilege to be here. And it's exciting to be here in Portugal to see so many people envisioning just this exponentially increasing presence in space. And it's exciting just to be able to talk to people here and be privy to those visions. And so thank you for inviting us to be a part of this. I'm going to extend a little bit on what Yvette introduced with the Institute this morning. Let's see. But, thinking ahead to this, a lot of what we do ties into the human aspects of spaceflight. And there's so much more to that. And I think of the greatest privileges I've had in life. Growing up with a career aviator, but also very much so being inspired from a very young age by astronauts, these explorers that are pressing the frontiers. What did that mean? From a very young age, I had an appreciation of education and of science. And you think of the things that astronauts return to the societies that support them. And here's a picture of one of our lead advisors, Captain Winston Scott. And astronauts fundamentally, they inspire generations. They serve to be ambassadors to STEM, because when you put humans in space, it takes all kinds of science that can be done, but all kinds of engineering and operations. Everything comes together, and there are opportunities to really expose people to just the wide gamut of everything you can do in STEM. So astronauts fundamentally are the face behind that. They're pictures of STEM. They succeed on the value of their own merit, not by other sources of privilege. What kind of person does a country invest its most brave missions to, broadly? They come with global perspectives, and they have this great sense of service. This is something we need more people with in all societies. It's one thing that brings us together. Space is such an incredibly unifying force. So how do we use space to build more bridges? And also, how do we use to tear down barriers? And this is fundamentally what our core values are when it comes down to it: science, stewardship, and inclusion. How do we get more people involved and represented in the scientific process? By harnessing this incredible inspirational power of the astronauts. How do we increase access? And by access, how do we make it so that students and young professionals have access to facilities that, have only been privy of a few countries so far? And how do we make sure that everyone's seen in this future too? As Dr. Sally Ride said, you can only be what you can. You can't be what you can't see. So a lot of what we do as an institute comes down to enabling human spaceflight. What do this new onset of vehicles present to us? And this is really exciting too, because there are incredible opportunities. The cost per pound is coming down. More countries are being involved. Universities, more people are experiencing and participating in space day to day. At the same time, we want to make sure that it's not seen as joyrides for billionaires. We want to make sure that it's seen as something that is inclusive of all, and that if we're going to be able to do these great things, like understand our climate, like go, be a part of Mars and therefore, then we have to all hit on all cylinders. We have to all be a part of this. So we look at what we do, and Aaron, Dr. Prasad, is going to talk more about the microgravity sciences aspects, bioastronautics, all of these come down, space medicine, flight test engineering is a part of our program, and the human factors that come with everything. Aeronomy is really where we started. This is our aeronomy program we also call Project POSSUM, Polar Suborbital Science in the Upper Mesosphere. And we try to understand the most sensitive part of our climate, that being our mesosphere, our lower thermosphere. One of the best places to understand things like global climate change, comparative planetology for low-density atmospheres on Mars, engineering reentry vehicles. All of this can be done. And the pictures on the right there, that comes from a NASA-funded experiment that had a lot of POSSUM participation on it, called PMC Turbo. The first time we've been able to observe turbulence and instability in our upper atmosphere at meter scale. Better place to see than anywhere else in the solar system. The middle pictures from Adrian Madui, one of our greatest science communicators within the program as well. And a first airborne, or first balloon-borne LiDAR system, looking at temperature profiles in coupling those with the imagery. So fundamentally, our aeronomy program, POSSUM, tries to understand better the nature of our upper atmosphere. But we involve citizen science in the students. Aspects here with one of our institute's aircraft. We go up in North Canada, to the right there, PMC Turbo. We have some support from the Canadian Air Force. It's the first time they've ever really incorporated with civilians in this way for research programs, incorporating their aircraft to ours to look at our upper atmosphere in different ways. So we got involved with spacesuits here in 2015. We were at first building instruments to study the mesosphere. We needed to build those instruments around the fidelity that one would use have in a spacesuit, whether it's pressurized or unpressurized. We started from IVA. We went ahead with EVA spacesuits, working under NASA Space Act agreement. How do you take technologies that work great in a lab and prove that they can work in a space environment? So a lot of what we do as an institute is integrating technologies to platforms to demonstrate this. So we're integrators, but we also are learning how to raise the technology readiness level. So taking it from it works fine in the lab to it works fine in space, and in the case of the spacesuit, you're willing to bet a life on. So here's a video showing the kinds of experiments we do. Now, if we could play the video, please. Here we're looking at range of motion. We're getting the test subjects, Kelly Girardi. She's getting her pulse rate up. An entire team is cross-trained, one for making sure that parabola, everything is safe. We're recording our biomonitors, our CO2 washout. At the same time, we're piggybacking about 20 other experiments, and many of these students run. Can we run the video on this? And train them to make sure that this goes safely. The other aspects of spacesuit, we could play the video on the left there. We're testing the suits, so if you have to, in the IVA suit, if you have a contingency, you'll most likely end up in water, whether it's on ascent aboard or if you check from a plane. Here's one of our members, Rick Blakeman. We got him a little bit hypoxic, and then we wanted to make sure he could activate the suit. We could play this video, please. Other aspects we do is the EVA suit. Here's a prototype EVA suit we've been working. One of the first steps we do is in gravity offset. So it's a facility that we have built and set up at the Canadian Space Agency. We also have in Melbourne, Florida. And the idea here is it can create anything from 0 to 1 Gs, and we can simulate lunar or Martian terrain and take everything that, say, Rui learns how to do in the analog field or contingency medical procedures, and we can then evaluate those in the suit in the appropriate gravity. If we could play this, this is Heidi Hammerstein. This is the very first time she's trying to learn to walk, and it's very different because your brain's telling you something different. So before you can even start evaluating suits or anything, you have to learn the simplest things, like how to walk.
Do you want to come down a bit? Or are you already happy how you are? It looks like an Apollo astronaut.
And then this is Neutral Buoyancy Laboratory is a representation of the Quest airlock on the International Space Station. Same mentality. Everything that we do, we have teams, our cross-trained test directors. Here is the first step. We're using low-fidelity suits, basically dry suits, AGA masks, and representative equipment. You'll see in the lower right the drone that's there to give the test director on the surface direct feedback to what's going on underwater. So, very much crawl, walk, run, as NASA says, making sure that that everything is safe step by step. Here's one of our campaigns with the National Research Council of Canada, microgravity campaign. We'll do maybe 20 experiments on each campaign, see how international the organization is. We have members from 53 different countries, and so it's really amazing to see how much space unifies everyone. And here's view. Here's Dr. Prasad will talk a little bit more, but I love this video here, so I usually show it on all because it gives you a really appreciation of the kinds of microgravity. As Aaron will say following me, even better than we get on the International Space Station. Okay, play this. Yeah. Perfect the formation can be, and you'll see, we stagger a lot of experiments. We're doing all of these concurrent with the human factor experiments, human performance experiments of a suited test subject. And so this is our last major campaign, the kinds of experiments that we had, but also in addition to all the experiments from the different students that came up with experiments that participate in the campaign. Flight test engineering is new to us. It's a great discipline for anyone in an operational professional. It mixes science, mixes engineering and operations. And so those that are getting into operational professions, it's a great analog. So it's something that came from, we recreated from University of Tennessee Space Institute program. It was the most popular program amongst astronauts in NASA and is no longer continuing. So a lot of the experts that came from there helped incubate this program within our institute. So in Melbourne, Florida is near the Kennedy Space Center. We have established the Gravity Offset Lab, the hyperbaric chamber. We have a spacesuit testing facility. The institute has 5 IVA spacesuits. 2 we just use for the pool, and then 3 for microgravity or for other applications. We have several aircraft that we use for different applications and different simulators, mostly for educational purposes. In Connecticut's where we have our neutral buoyancy lab and our egress lab. So it is a pool facility, and then in Ottawa is where we work with the National Research Council for the Falcon 20 microgravity aircraft. So we're partner with NAUI, which is International Scuba Association. But a major part of this is education. So a lot of what we do matrixes, as Yvette had said, matrixes in younger students with professionals. And so people learn together, and one of the major things in the Institute is not a grade-based feedback system, but more, can you lead, encourage people, as young as 18 or 19 that come in, encourage them to use these opportunities to lead and publish their own professional publications. So having access to these facilities, it's one of the strongest things we can do is create access for our youngest members, our youngest students. So right now the Institute has licensure from the state of Connecticut, which is the major step in the process of national accreditation, which is pending. We're anticipating that within 2 years, at which point we are targeting 3 masters and 4 professional certificates. So, education, inspiring the next generation. Some of our younger members there that come through our academy class, which is a feeder class for undergraduates. And there's Winston Scott giving some of his spaceflight experience to one of our British members. And and as Yvette talked too, we have 3 outreach programs very specifically targeting underrepresented minorities. Space for All Nations is when we are very excited here about trying to find ways to build collaborations between institutes within emerging space nations to work together, but also create access in ways with the networks where we there's a few of our members, one that's been to space, one that's going to space, and one that is impressing your prime minister. So
Thank you, Jason. Please join us. Please join us. And next, we have another colleague from the IIAS. Dr. Aaron Persad will join us. He is a research scientist at MIT, and he's also our very own Director of Bioastronautics and Microgravity at the International Institute for Astronautical Sciences. His research actually focuses on the size separation of molecules using novel filters made of graphene and angstrom-sized features for applications in healthcare, energy, and water purification, all relevant to everything we've spoken about. Today, Aaron is going to talk about our bioastronautics reduced gravity research and human-in-the-loop environment for experiments. So, Aaron, to you.
Thank you. All right, so while I'm waiting for the slides to come up, great. That's it. Thank you. I want to thank the organizers, Anna, Rui, Sophia, Paula, many who worked behind the scenes. This is my first time in Portugal, first time in Porto, but seeing so many familiar faces already, it feels like I'm home. So I want to thank everyone for such a warm welcome and opportunity to be here. So the talk I'll be giving today is bioastronautics and research in the reduced gravity environment with a specific emphasis on human-in-the-loop testing. And my subtitle is A Shift from Autonomous Payloads Toward Human-Tended Payloads. So what we'll talk about today is what is microgravity in space sciences. We'll talk about the commercial, non-governmental opportunities that have arisen recently for human spaceflight, and what the IIAS is doing to prepare the next generation of spaceflight participants to be effective researchers on those new vehicles. And then I will zero in on the reduced gravity research that we do in particular at the IIAS, and also highlight some of the STEAM outreach. So you're probably familiar with science, technology, engineering, and math, and we'll add the A for art. So that's also an important element. So what is microgravity? I think part of that answer is understanding what is gravity. So on Earth, we're familiar with gravity holding us, on the floor. And if you want to figure out, okay, like how is it doing that? You go back to Newton's laws of motion, and there are two forces that balance themselves. And if you know the size of the Earth, the mass of the Earth, and the universal gravitational constant, you can actually calculate the acceleration that you're feeling right now. It turns out to be 9.81 meters per second squared. And I want to highlight that this bolded number, the universal gravitational constant, is extremely, extremely finely tuned. What that means is that if it's slightly higher, the universe collapses, and if it's slightly lower, the universe expands. And so life, this is just one of like a dozen or a score of numbers that are so immensely fine-tuned, and microgravity sciences is one way to sort of deep dive into those phenomena. But this value of 9.81 is not necessarily the only acceleration field that you can feel, depending on where you are on the Earth or within the Earth. So what this is essentially showing, these plots, is that as you move from the surface of the Earth to the interior, depending on the composition of the Earth, the planet, we saw Rui talking about the moon, its sort of composition, while the Earth has different like crust, mantle, and core, and the models that you use for those can impact the number that you get, essentially, for where you are. And so when you look at the Earth, this is a closer picture of what the gravitational field feels like, depending on where you are, and that's going to change with earthquakes and so on and so forth. So it's a changing number, but it doesn't change all that much. So for all intents and purposes, 9.81 meters per second squared is what we feel. So we still haven't answered what is microgravity. So I have a photo here of Julie Payette. She's a retired astronaut, but she's floating on the space station. The question is, what makes her float within the space station, right? So Well, we look at the space station, you might be tempted to say, well, she's floating because it's zero gravity. Well, the space station is 400 kilometers above the surface of the Earth. And so if we go back to those math equations and plug in the numbers, what we find is that the acceleration that the space station feels is not zero, it's 8.7 meters per second squared. So actually, we're like 90%. The space station is feeling 90% of the acceleration that you're feeling right now. So that is not zero gravity. And by the way, the Earth is held in orbit by the sun. And if you put in the mass of the sun, the distance between the Earth and the sun, what you find is that 0.0061 meters per second squared acceleration is what holds the Earth in orbit around the sun. So basically, if it were zero, like we don't have Earth orbiting the sun, but even a tiny amount of acceleration can have a huge impact. Like only a tiny amount is what keeps our planet in orbit around the Earth. So what I'm getting at is it's really important to be precise and accurate about our language. So here I have a girl in a supine position, roughly the same pose as Julie Payette, but that girl is not floating. Why not? So let's do a free body diagram. So for the girl, she's like that box on the table, and there are two forces that are acting on her. There's the weight, her mass times the gravitational field, that's acting downward, but the table is exerting an equal and opposite reaction. And so the total force is just zero, and so she's not moving anywhere. What happens if you remove the table? Her weight is still there, right? The G doesn't go to zero, but what you lose is the normal force. And now all that she's experiencing is her weight, and so this is exactly the scenario that Julie Payette is in. And so you too can experience exactly what Julie Payette is feeling just by jumping up. The moment your feet leave the ground, you are in free fall, and it's the same sensation, the same environment of being in free fall on the International Space Station. To me, that's wild. It's like you don't have to go to space to be in free fall. You could do it right here on a trampoline. All right, so now let's get into this question. What is microgravity? So a lot of G's. So, grams, universal gravitational constant. These italicized letters. G would be relative. Sometimes we use 10 meters per second squared because 9.81 rounds really nicely to 10. But to be precise, we'll have a G naught, which is specifically referring to Earth's gravitational field. And then sometimes we'll talk about an effective gravitational field where you have like air drag and stuff that's impacting your experiment. And so when someone says, I do microgravity research, what are they really doing? And so it's not obvious from the literature exactly what someone's talking about. So technically, yes, it's 10 to the minus 6 G zeros, or 1 micro G, or 10 to the minus 6 meters per second squared. If you want to be technical, that's what micro G is. So physically, and I think this is probably the most accurate definition, is it's the absence of a normal force when you're in the presence of a gravitational field. It's incorrect. Hopefully I've convinced you that it's not 0 G. And we often will use the term near free fall. Why? Because there's air drag, friction. Sometimes the space vehicle will jitter and vibrate. So we say near free fall because we acknowledge that it's not quite perfect free fall. And you'll also hear the term reduced gravity, but reduced gravity can also include Martian and lunar conditions. So now that we've talked about what is microgravity, the question is, why do we care? And so this was taken from the European Space Agency's website on their definition of what is space science. All this stuff that we've looked at, planets forming, the moon, astronauts in space, that's all space science. Why do we care? This is why we care. We want to understand where our Earth and solar system came from. We understand where we are in the universe, where we're going, and very importantly, where did life come from, and are we alone? To me, these are very philosophical questions to have been posted on the European Space Agency website. It's like a degree in philosophy almost. But the ancient Greek had a word to capture this, and it was a statement, the reason why, and it was called logos, the logos. And if you think of like biologos, biology, the reason why living things are the way they are, cosmology, cosmologos, the reason why the heavens are the way they are, that's where that word comes from. So space science is answering seeking to answer the question to the reason why. All right, so you can do experiments in near free fall at home. And here's an example of an experiment where I took a toy, an executive toy, probably seen this, oil droplets rolling down a ramp. And all you do is I had a GoPro camera and my object, and I threw them up. They're attached together. And I get about 1 second, but in 1 second, you can do a lot of science. And I used my phone to capture the acceleration so I can go back and track, the G levels. But these are some screenshots. Let's look very quickly at it. In 1G, the oil droplets are deformed. They're not quite spherical. They're rolling down the ramp. And the shape that they have, you can see that the bottom shape is different than the top shape. But the moment I put this system in near free fall, just throw it up, what happens is the droplets, you'll notice they actually bounced off the ramp and then stopped. And so the reason they bounced off is that this is under compression. There's tension that's built up from surface tension. In reduced gravity, the surface tension forces now dominate over the inertial forces. And so the droplets will spring up from the ramp, but it's springing up in a fluid, and the viscosity slows it down and stops it at some point. So from this one experiment in 1 second, I now have some data, and I can learn about the role of gravity on density, buoyancy, miscibility, and all of these different parameters, etc., around outer space, right? And so these are examples of how you can bring a near free fall platform to your home, your school, museum, university. You don't really have to go to space, which is amazing, but there are advantages to doing things in space. So when you do research in microgravity sciences, you want to access different platforms. Sometimes throwing something up in the air is not enough time, 1 second. So we use drop towers. So essentially a 10-story tall building, you drop your payload and you get about 10 seconds of microgravity time. What's the downside is when it lands, you have a high impact, almost 15 Gs. So your payload has to be really robust to survive that. You can also fly your payload on a balloon, and then when it reaches altitude, you release the payload, it falls, and then a parachute deploys. So you get about, again, like 8-10 seconds, but the Gs of the landing are much more manageable. The other platforms are sounding rockets. So if you need, let's say, 10 minutes, 20 minutes of time, you can launch a sounding rocket into space. This typically is what the rocket looks like, and sometimes they can actually go higher in altitude than the International Space Station. Now, in all of these platforms I talked about, throwing something up, a drop tower, sounding rockets, a balloon, you can't have a person involved. So your payload has to be automated, and it really limits what you can do. And it's the same thing with a recoverable satellite. This is the gold standard for physical science research. If you have an experiment and you want to have the best reduced gravity quality, you do it on a recoverable satellite that is round. It minimizes the vibrations, you get really good quality, and once the satellite lands, you can recover your payload and do your analysis. Again, no person can really fly in here. So the only platform up until recently that was available to do human-tended research was the International Space Station, but the problem is there are a lot of movement and vibrations on the station. And so astronauts are exercising, running, making a lot of noise and vibrations. You have fans and doors and solar panels that are moving. And so if you look at the G levels here, rarely are you hitting 10 to the minus 6 meters per second squared. You're more likely at 10 to the minus 2 meters per second squared. And so it's actually one of the worst environments to do your experiment because you're not really going to be hitting the G levels that you're hoping to. So now we have suborbital vehicles and orbital vehicles that are available, and these open the door for us to do something that has been very difficult to do before, which is, one, have human-tended payloads, someone in the space vehicle operating my payload, but secondly, I can free float my payload in the vehicle. What that means is now my payload isn't being exposed to the vibrations of the vehicle. So I can achieve an amazingly good reduced gravity environment, and then the person is there to sort of grab it and reset it and keep going. So the door that's open to do high quality science is tremendous here. So one of the things that we do at the IAAS is plan for access to that environment. And to get an experiment flown to space, you need to advance its TRL, its technology readiness level. And so in parabolic flights, we'll target TRLs of 3, 4, 5, and 6. And this is showing a parabola where the aircraft flies level. It climbs up like a roller coaster at 2 Gs, so you feel twice as heavy, immediately pivots down and free falls for about 20, 25 seconds, and then recovers at 2 Gs and does it again. So that's what you're seeing here. And as Rui was talking about moving in a spacesuit, even without a spacesuit, moving around in a different G environment is very, very challenging, and you need to practice. So there is a TRL of hardware, but we need to think about the TRL of a person that's going to space. How to get them familiar with how they react and work in space, giving them the hands-on experience, de-risking that person so that they're very effective and focused on their mission, know how to deal with off-nominal situations, and probably the most important thing for me is gaining muscle memory, knowing how to move your muscles in a free-fall environment so that you're not over-moving, overcompensating, and you're really precise in your motions. Rui talked about flipping switches. You have to relearn all of that. And the whole goal is to make them effective payload specialists to maximize science. So one of the ways that we de-risk is train, train, train. So here I have some examples here where we've got our neutral buoyancy lab that Jason talked about, and we're using a rover to communicate with the EVA astronauts, send signals, and communicate back to mission control. And this is an amazing scenario where we're linking robotics and people on a mission with a human in the loop and looking at what could that look like in the future in space. I think that's an incredible thing. Jason talked about walking in a lunar gravity. So this was Shauna, her attempt of walking. And we'll take some of the tools that we developed in the course EVA 103 that Rui talked about, bring them to the CSA's lunar yard, intergravity oscillation system in the spacesuit, and try them out in that scenario. And we learned so much about how to design tools for use for planetary exploration. So now, talking about microgravity sciences, Jason showed this video already. And what I want to just highlight here is that we designed a controller for the person in the spacesuit to use pressurized, fine buttons and knobs and things to turn to see how precise they could be with a spacesuit in this environment. And so with a lot of training, we can get someone to actually operate some really fine controls. I have an example here of Heidi doing a VR test for Shauna. So bringing VR into the into reduced gravity environment, how does that all feel and work? It's amazing. And then here we have a satellite that's being deployed, the solar panels, and we're testing out how that works in the freefall environment. One of the many experiments that we had talked about. So in our flight campaigns, we advanced the TRL of our spacesuits and life support system. We went from scuba tanks to air blowers and so on. We added flight controls and even revised the spacesuit to be higher fidelity and ready for spaceflight. This is an example of our seats. We went from like an airline seat with a harness to a very customized seat that could be integrated to a spacecraft. And then we went from scuba tanks to air blower systems. So these are some examples of the research that's being pumped out from our campaigns. And then drawing to a close here, we also collaborate with industry. So this is the Astroskin from Current Technologies in Quebec, Canada. And they basically built a smart shirt that monitors how astronauts perform in space. One of the complaints that astronauts has is they don't want to take time out of their day to fill out a survey. And they don't like sensors that are intrusive. Give me a comfortable smart shirt to wear, let it collect the data on its own, and that's easy for the astronauts. So what we did was we actually tested out this Astroskin smart garment before its flight to space. This was the first time it was tested in a microgravity environment, and we were able to identify some bugs that had to be worked out prior to launching to space. So Shauna has it on under her spacesuit. We tested out a new cap that has a blood saturation sensor on the forehead. Normally it's on the fingertip, but astronauts use their hands a lot, so we moved it to the forehead. And then after all of that work and testing, it flew to the International Space Station, and it's currently there and being used by astronauts. So this is an example of the pathway we make available to researchers to take something from idea and concept all the way to getting it to the International Space Station. Jason showed the fluid cells, but I'm going to show you this one. This is the fluid cell attached to the aircraft. Jason showed the one where it wasn't attached to the aircraft. So let's take a look. Maybe you might have forgotten, but see if you can spot any differences between what he showed and what you're seeing here. Kelly Girardi is back there doing her thing in free fall. So you recall Jason, when he showed the video, things looked a lot more symmetrical than what you're seeing here. And so this is showing the effect of the aircraft on the fluid behavior. Just attaching it to the aircraft, even though the aircraft is in free fall, the vibrations of the engines and wings is causing the liquid to behave differently. I'll skip over this one. And so this is a comparison. This is what the interface looks like during the climb, 1.8 Gs. This is when it's attached to the aircraft, roughly 10 to the minus 6 Gs. Normally, the scientists would be very happy with that result, but we're able to push it further, free float the payload, and you can see the difference that 10 to the minus 6 versus 10 to the minus 7. Actually, 10 to the minus 7 is what you need to get it to match the physics. And so a lot of experiments that are done on station are 10 to the minus 2. So we're discovering and pushing the boundaries of the cutting edge microgravity research. And then we talked about the moon. I don't know if you know this, but when Buzz Aldrin and Neil Armstrong landed on the moon, Buzz Aldrin brought with him Eucharist, communion. So he had the wine and the wafer, and he poured the wine into a silver chalice, and he had his wafer. And so we did an experiment where we just studied how does water look like in a lunar environment. And I think this is spectacular. It might loop back again. If it doesn't, let me play it back. I just want to highlight, it looks like molasses. when the liquid is flowing, it looks viscous, it's blobby, but if you touch it, it just behaves like water. And it's so counterintuitive of how water looks like in a lunar environment. Is you can think about drinking on the moon, cooking, eventually what all of that looks like, and how we have to relearn and retrain ourselves, that muscle memory I talked about, to get working in that environment.
We have 2 minutes.
Ooh, okay. So I've got 2 slides. So with access to this wonderful aircraft from the National Research Council of Canada, based in Ottawa, Canada, we open up the aircraft to invite STEM outreach activities. So the Possum 13 that Yvette mentioned, we have a program or competition where we target high school students because they normally do not have access to parabolic flights. And we target female-led high school teams, ideally from countries where they don't really have the opportunity to do this. We run a competition that's called the Possum 13 competition. We collaborate with Space for All Nations to get communities involved. We provide translational services if there's a language barrier. And we select some of the top payloads and bring the student, we fly the students over to Canada and let them fly their payload in the aircraft. So our winner in 2000, I think it was 19, was Ivana Hernandez from Colombia. She was 16 years old at the time she flew, right out of high school. And she joined our flight campaigns with all of her researchers. And this is what she said, that in her country, women are not often viewed as engineers and scientists and so on, more likely as singers, actors, dancers. And she wanted to change that perception. And so this is her, this is the last slide, flying her payload on the Falcon. So I think that's going to be a life-changing experience for her. And I have here all of the people that work behind the scenes to make things happen. And with that, I say thank you for your attention, and feel free to email me right there.
Thank you, Aaron. Please join us. Yeah. It's always exciting. In fact, she was still in high school. So impressive. And as we've explained, I mean, you've seen
our microgravity work, our nutribuoyancy lab, our gravity offset, but we do extend that research to space medicine. And while Dr. Shauna Pandya couldn't be here today, she is in the country, she sent us a message. So let's look at this video and hear her message about space medicine.
Hi everyone, my name is Dr. Shauna Pandya and I am a Canadian physician, scientist, astronaut candidate program graduate, lead instructor for the Operational Space Medicine course and director of the Space Medicine group at the International Institute for Astronautical Sciences. And I am so excited for the workshop that you are all going to be part of today. Congratulations, Anna, on putting together such a wonderful event for people who are interested in space, especially with Portugal being an emerging space nation. And the reason I'm so excited for you all is because this is the best possible time to be involved with space. On the commercial side, there's a lot happening with suborbital spaceflight, with orbital spaceflight, and on the exploration mission class side, we see all the world's major space agencies setting their sights on the moon, Mars, and beyond. So if you, whether you love space medicine, whether you're passionate about technological advances for enabling human space exploration or robotic exploration, or whether you're just curious, this is the place to be. So you are in for a wonderful day, and I am so excited for you. Congratulations on being here, and make the most of today. Enjoy your day.
Let me say something which is important and a fantastic lecture from the microgravity. I learned something today. But let me just announce that tomorrow we will select 30 students to fly microgravity in 16th of September here in Portugal. So we have this campaign. But let me tell you more. Even yesterday in the GLEX, it was announced that we will have the first commercial, I think we should say like that, commercial astronaut, right? Because it was a Portuguese that will fly in the commercial flight in suborbital. And it was announced to yesterday in the GLEX summit. So it's something that for our country is a challenge also. So we'll pass to Andrea Oliveira. Andrea Oliveira is a PhD student in biomedical engineering at the Faculty of Engineering of the University of Porto. Please come to the stage. And she's a researcher at the Neuroengineering and Computational Neuroscience Lab in I3S, I should say in Portuguese, Institute for Research and Innovation in Health, Porto. And today Andrea is going to talk to us about the field of space medicine. Thank you, Andrea.
Hello, everyone. First of all, thank you for the organization, for the invitation to be here. Okay, so I'm going to talk about space medicine, but also about space medicine here on Earth. And I want to talk to you about the so what of space medicine. The so what is something I learned when I was preparing my thesis 2 years ago. In medicine, I was studying research, surgical care in low-income countries. And I was discussing with my colleagues, and they were like, okay, so we're planning surgery in low-income countries, but so what? They have more pressing issues in terms of health-wise, or even not health-wise. And that was a reality check that in health, particularly in health, investments have to be very well justified. And what I hope that I get from this talk today is the so what, why space medicine is important, not only for space exploration, but also for health here on Earth. Space medicine, well, health is so intercultural, so holistic, because we're not just talking about human bodies, we're talking about people. People that have needs, that also have fears, that have, well, us. And human bodies are one component, but we have to take into account all other components when we're designing experiments, when we're designing settings, when we're studying space health medicine. But also because we're talking about space exploration is probably the field that most needs of collaboration, even between nations, between cultures, but as well between disciplines. But let's go back to health and space medicine. As you see, clinical aspects are just one tiny aspect when you think about health, and the person also is one of the components. when we're talking about space medicine, we're talking about environment, we're talking about research. So we're planning a mission to Mars. How are you going to have medicines, or how are you going to evaluate the symptoms or the state of the patient, the persons that are there? So we have to work together alongside with all of the disciplines. We have to take into account the vehicle, the environment, even the specific needs for each mission. But well, part of it is about the human body and the clinic aspect. The first effect will be adapted effect to an environment that is not health. The first thing that probably is more emergent is microgravity, but there are also other aspects that we need to take into account, for example, radiation. Moreover, we don't know the exact long-term effect of being in such environment. So besides the adaptation symptoms we're going to have, we need data, we need experiments to understand, to predict in long term how will the human body behave. And in terms of the human body, well, the human body is composed from several systems. So each system will have their own adaptations, and we have a caveat, that is the metrics that are most useful for us here on Earth, which is the symptoms, won't behave in the same way in space medicine. For example, a headache probably won't be for the same reasons, or even the characteristic of a headache won't be the same for a person here or a person in space. So we not only have to study the adaptations, we have to relearn how the symptoms behave. How can we evaluate even the state of the person that is there? And we have three main categories where we focus that on. We have the first one, which is the clinical, most objective aspect, but also take into account the human performance. So it's just not about, we call it physiological symptoms, but also cognitive symptoms, behavior, and also about human system engineering, where we take into account the environment and also mission planning. All the parts are not completely directly to the human body, we also take into account. So these are the three main categories. And well, this is the broad overview on space medicine. We have three specific areas of applications when we are, let's say, practicing space medicine. The first one is research, education, and research, because, well, everything starts with education, not only for health professionals, but also for other professionals. And research is particularly important because what I've said, that we don't know how the human body behaves long term, even for every situation, and it's quite a valuable data and hard to collect one. So research and education goes the foundations for what we're going to work on. We can also be flight surgeon. Flight surgeon is, well, the doctor not only in terms of, in this case, the astronaut, but also in many cases it follows the family of the astronaut in other conditions. So it's not just about the mission itself, it's more broad than that. And lastly, when you talk about space medicine, and even more broadly to aeronautic medicine, we also talk about certification, because one important step is the selection of the persons that are going to fly either astronautic or common flights. So certification is also one of the fields that it's studied in space medicine. So what are the future challenges? We have to increase education and research in such a setting. And I'm also almost going to the so what. We also have to overcome this limitation of implementing protocols in terms of how can we better design them for being coherent with other research, so that it's not a standalone protocol, so we can gain from other fields. And lastly, what I think is the so what. Well, I don't know what the future holds, but as a doctor, I'm pretty sure that almost all my patients will be humans here on Earth. And what I think is the so what of space medicine is, by going abroad out of the Earth, by exploring and learning more for space exploration, we're actually expanding knowledge from the human body. That is going to be quite valuable here for us and for our families and for the people we know. So space medicine is not just about space exploration at all. It's about making health better here on Earth. So I think that's my so what for why space medicine is so important. Just quick note of what's happening here in Porto. In the University of Minho, we're starting a subject on space medicine next September, where the students will grasp some concepts but will be challenged to design a project to be implemented in a space mission. And there is also some emerging research, either in human factor and behavior performance, also team performance, and more coming up soon. A special thank you to Dr. Gonçalo Torrinha, Pedro Caetano, Dr. Pedro Caetano, Dr. Pedro Quintero, and thank you for your attention.
Thank you, Andrea. It seems that we're starting to have a small ecosystem of space medicine in Portugal. I'm really glad to hear that. And it means that to the visit to other planets, the importance of space medicine, and probably we'll raise some questions about that, because it's quite complex, our permanence in space. And to travel long distance, particularly to go to Mars, space medicine plays its role. So I open the session now to Q&A. I also received the instructions to be receive 1 or 2 questions. So, but please, if someone wants to raise a question, don't be shy. Microphone, please. And go to the point to be fast, please.
Okay, it's for the medical school in Minho. In your research areas, have you considered balance disturbances from people that have been bedridden? They lose muscle mass, similar to what happens in reduced gravity exposure. Have you considered that possibility? I've worked for 10 years in that area, and maybe there might be something that could be done.
5 seconds. It works? You
I'm actually not a research in Minho. I'm a research in University of Porto. I'm only assisting in the educational part. But from what I know from my colleagues, they are considering studying bed rest. I don't know how much in depth they have been into the topic, but the person to ask is Dr. Gonçalo Torrinha. He's the one who's motivating the research in Minho.
So I have a question about how different is neurotransmission in space? Are there fundamental differences in how the synapses function, or do we only expect there to be differences in the inputs when it comes to proprioception and other sensory experience?
Well, okay, a step back on answering to your question. How can we study a neurotransmission in space? Because here on Earth, we do patch clamp, we do in vitro. That's very complicated to do in space medicine. I'm not aware in literature of having studies on that specific topic. We'd have to go to tests where we could not be invasive, but that way we would make assumptions on how the transmission is being done specifically in space. But there are some studies with EEG. However, your specific question, how neurotransmitters within synapse behave, it's very difficult to tackle in such environments.
Oh, I received permission to ask a question. And this is for both Jason and Aaron. And I think it's important to understand now that we have commercial space, and active commercial space, is temporal data important? And I ask because you mentioned that in 1 second, you had enough data to do an analysis. And people are asking, why would I choose to do my science on a suborbital, which is 3 to 4 minutes, versus ISS, where I can go for weeks, And what is the value of time?
Yeah, thank you for that question. So there's a trade-off between cost, complexity, access. So the 1 second example, anyone can do that, but you're fairly limited in the type of study you could do. On a parabolic flight, 20 seconds sounds like it's a short amount of time, but it's enough time to answer this question: is my payload ready or not to go to space? Oftentimes, that's what a parabolic flight is used for. And then once you're in a spaceflight environment, you're increasing your time now to 2 minutes, hours, or days or weeks or months. So the question becomes, if you have a study, which is the best platform to use given your objective? So the fluids experiment that we showed, the fluid cells, for now, I think 4 minutes of free fall time should be enough to answer the question. But to answer a question about like how the neurons conduct in your brain, you might need a couple days at least to set up the researcher and the patient to do that. So it's not an answer for everyone, but what's great about it is there are options available for the scientists. The more options that are available, the better it is for everyone.
Thanks, Aaron. I'll add for that, there's unique capabilities that each kind of platform brings. We see the onset of suborbital vehicles. One right away when we talk about the POSSUM program is to understand better our upper atmosphere. And before then, actual in situ measurements could only be done by by sounding rockets, and you get one flight on those, and they're often a couple $1 million US to fly. Here you have a reusable vehicle that can repeat measurements, have stabilized imagery combined with in situ measurements, and that is something that just hasn't existed before. So if you're studying things like our upper atmosphere, it's a very unique piece of the puzzle that can't be done by balloon or aircraft, can't be done by orbital vehicles. Aaron, you also alluded to the time to effect of different experiments. Yes, some things you can't do in parabolic flight because you only get 20 to 25 seconds of exposure. I was just having a talk with you this morning about procedures, medical procedures, for example. I think the example I was using was inserting a chest tube in someone if they had a pneumothorax or empyema or something in long-duration spaceflight. Well, a suborbital vehicle gives you about 3 to 4 minutes where you could validate procedures like that in a way that you just don't have enough time in parabolic flight. It would be much, much, much more expensive to try to specifically do on an orbiting platform. So there are many different things that these bring to the table, and we're really excited to see more research being applied to these vehicles, like see how we integrate things into the parabolic flight, incorporate all sorts of education and outreach platforms to existing primary and secondary payloads. The same kind of methodology could be done to suborbital flight to greatly increase the overall impact to unique experiments, but also involving many more research and educational organizations.
Let me recap something, which is your words, Jason, when you did your presentation. I took my notes here, and I really want to say this, because you mentioned that how astronauts serve the society and brings the perspective of the international collaboration and diplomacy. It is something important, because we are now, in particular from space, fight against the unglobalization, and space is a diplomatic tool to international cooperation. And also by Aaron to say that we are here because the constant of the gravity, right? No more 1 centimeter to the left or to the right. So thanks to the gravity, it's possible to be here. And we are moving, right?
Thank you. And I will say, as somebody who constantly drops her food, gravity is not my friend. So now we're going to have a series of videos from our colleagues who couldn't join us today. So I'm really excited about the next one. We've talked about how space matters and all the options we have for space research. But now we're going to talk about our technical developments for deep sea, which is one of my favorite places as well, to Earth observation and outer space. So our first one comes from Hunter Williams. He's the Technology Development Manager at Honeybee Robotics. It's a Blue Origin company. And he's recorded this message for us.
Greetings to the attendees and audience of the Bio, Geo, and Tech Come Together to discuss the current frontier of space exploration workshop, as well as everyone working together as part of the Portuguese space ecosystem. My name is Hunter Williams. I am the Technology Development Manager at Honeybee Robotics in Pasadena, California. Honeybee Robotics is a subsidiary of Blue Origin, and we build space mining robots. We at Honeybee are excited about the future and the potential for collaboration with emerging space nations such as Portugal. Small entities with limited funding, relying on creativity and people power, can do much. When Honeybee was still a small business, our tools were the first to touch the inside of a Martian rock and the first to sample ice from the Martian surface. In the near future, we believe countries such as Portugal will be an integral part of efforts to establish permanent human presence on the lunar surface, providing key elements to internationally run systems such as the Lunar Electrical Grid and the Lunar Propellant Value Chain. Future in-space resource utilization operations will enable human habitation and robotic exploration of planetary bodies throughout our solar system, starting at the Moon, going to Mars, asteroids, and beyond. Small businesses, emerging space nations, and large established players in the global aerospace industry will work together to make this dream of traveling and living beyond the Earth's surface a reality. Peaceful international collaboration is the key to exploration of our solar system. We at Honeybee have had fantastic experiences collaborating with international partners such as JAXA on our mission to Phobos. We look forward to one day working with you in the same capacity. Thank you.
And now we have a video from Lori Magruder. She's the Associate Professor at UT Austin's Aerospace Engineering and Engineering Mechanics Department. And she has extensive experience in remote sensing and 3D geospatial data exploitation for Earth. We'll listen to her words.
Hello, my name is Dr. Lori Magruder. I'm the Associate Director at the Center for Space Research and an Associate Professor in the Aerospace Engineering Department here at University of Texas at Austin. I'm excited to present to you today and be a part of this workshop. I'm not excited not to be there in person, but I really appreciate the opportunity to record a video and contribute to the workshop. Today I'm going to talk about NASA's Earth Observing Laser Altimetry mission, ISAT-2. ISAT-2 is the Ice Cloud and Land Elevation Satellite 2. It's the second. It's a great example of some state-of-the-art technology and that engineering as it bridges to some amazing scientific discoveries as we collect data about our Earth's surface and Earth processes. So I hope that you'll enjoy this talk and also gain some knowledge in terms of this particular mission. You might ask about my qualifications to talk about ISAT-2. It is a NASA flagship mission and primarily out of NASA Goddard Space Flight Center. But we actually have a really large ISAT-2 research footprint at the University of Texas at Austin, one of the largest outside of the NASA facilities. I and my colleagues have been members of the science team since 2009. The science team is a selected group of subject matter experts by NASA to advise the project and headquarters on the design and development of the mission, as well as on-orbit operations and data product quality, kind of all aspects in every phase of mission lifecycle. I've been the principal investigator for 5 years of the precision pointing determination team. That's an operational support team and part of the data product production pipeline, if you will. Also with that pipeline are data products associated with science applications and surface discoveries, mostly associated with terrestrial ecology and also bathymetric science. We have a lot of strategies or techniques ongoing to monitor the performance of ISAT-2 and validate that the data is the correct quality to feed all of the scientific derivations and discoveries that are able to be made. A little bit of background about ISAT-2. As I said, it's a Earth Observing Laser Altimetry mission. It's the successor to ISAT. That was the original laser altimeter that was operational from 2003 to 2009. Now, both of these missions had primary scientific objectives associated with the cryosphere. And those were through recommendations of the Earth Science Decadal Survey that's released every 10 years. For ISAT-2, it was released in 2007, and the recommendation was to put priority on quantifying the cryospheric contribution to global sea level rise through changing climate conditions. And it went on to recommend or point out that laser altimetry was the ideal technology to use in terms of elevation accuracy and product quality to quantify these changes and add to the time series that ISAT had already created. Through that concept development in 2008, we launched 10 years later in 2018. We've had more than 1 million measurements to date. All of those data, every terabyte per day, after 1,391 days, is available to anyone in the world at the NASA Data Archiving Center National Snow and Ice Data Center. Can be found at nsidc.org. Now, in terms of altimetry as a measurement concept, that's pretty simple. You precisely measure the travel time of the laser pulse from the instrument to the surface and back to the instrument. That gives you a range between the instrument and the surface. That is a magnitude of the pointing vector that you can get through understanding the orientation of the satellite. And as long as we can use positioning of the satellite through GPS or GNSS technology, then we put those two vectors together so that every pulse of the laser will give us a latitude, longitude, and elevation of where that beam impacted the reflected surface. ISAT-2 had the advantage of leveraging many lessons learned from ISAT, the original mission. Now, the challenges with ISAT was that it had a heavy, high-powered laser that produced one beam with a pretty large footprint on the surface, about 70 meters in diameter. And that large power laser operated at 40 hertz. So given the 500-kilometer average altitude, that gave us a measurement in the along track direction every 172 meters. So we were missing a lot of that high-resolution feature detail because of the granularity of the measurement. So that was a challenge. Also with one beam, if you're not hitting precisely at the same position given repeat measurements, then it's really hard to disentangle surface slope from true elevation change, which was the crux of the mission, particularly over ice sheet. So to answer those challenges or alleviate those challenges, then ISAT-2 used a new technology called the micropulse multi-beam photon counting approach. And that detection modality is, as it sounds, it's sensitive on the single photon level. So we can use a lower power laser. And because we have a lower power, we can divide what energy we do have across multiple beams, as well as operate at a higher rep rate. So ATLAS, the instrument, which is the Advanced Topographic Laser Altimeter System, our photon counting LiDAR, it operates at 10 kilohertz, which, given the similar altitude of 500 kilometers, we will get an along track measurement every 70 centimeters. This is quite an improvement in terms of a long track resolution from the previous mission. We also have, within the multiple beams, have different beam energies so that we're able to explore or really collect more optimal data associated with different reflectivities of the surface. So saturation isn't as much of an issue here that we also experience with ISAT over highly reflective surfaces. Overall, we just have improved accuracy. We're able to discover those fine resolution or fine feature details, and it's made a big difference in terms of mission operations and pleasing the scientists, I guess. Here's what we have in terms of beam configuration for ATLAS. The 6 beams, we have one laser operating. That one beam goes through a diffractive optical element and produces 6 beams into 3 beam pairs. That each of that pair contains a high energy and a relatively lower energy beam, about a fourth of the energy level. Within this beam pair, the weak and the strong beams are separated by 90 meters in the along track direction, but then each of those pairs is separated by 3.3 kilometers from the other pair in the cross track direction, excuse me, the 90 meters in the cross track direction. But we still are getting the 70 centimeter resolution for each of the 6 beams. In terms of coverage, it's quite a significant change from ISAT to ISAT-2 with this multi-beam configuration. You can see in the upper left the ISAT coverage over Jakobshavn Glacier, and this is for one 91-day repeat orbit. So each of the satellites had a 91-day repeat orbit cycle. Within that 91 days, each satellite would, well, for ISAT-2, completed 1,387 orbits. And once you reached 1387, then you would go back to orbit number 1. This gave us an understanding of seasonal variability. ISAT-2 had a similar repeat cycle and subcycle. But you can see here the coverage with the red lines in terms of corresponding to coverage areas or long track collections compared to the 6 beams of ISAT-2 shown on the right. It was a significant increase. Also, what I can say is that they were both near polar orbits, but ISAT-2 was is at 92-degree inclination, that's the angle from the equatorial plane, and ISAT was at 94 degrees inclination. This meant that ISAT-2 achieved 2 degrees more in latitude coverage on both poles. So we're getting coverage from 88 north to 88 south. So we're starting to fill in those pole holes that we experienced previously. And these are really hard to reach areas, and so the data has been very exciting and is filling a current gap. I like this movie because it shows you, it'll play. Well, that's laid plans. I'm not able to play my movie in this video, and I'm sorry about that. But what I wanted to illustrate here is kind of the context of these 6 pencil lines of ISAT-2 collections along the surface. And since the laser operates continuously, we're getting elevations over a variety of surfaces to serve a broad scientific community for sure. And although the coverage, the coverage of these beams is somewhat limited, they really have been a significant and transformational contribution to 3D products where we get the wide geospatial coverage of imagery or spectral products, that these provide very accurate vertical seed points, if you will. So a lot of the new science has been due with data fusion and conflation of these data. Now, as I mentioned, the multi-surface collections serve a broad science community, and the mission itself produces data products, along track data products using these data specialized for each surface. So if we look at these data products, one example I want to draw your attention to is here in the bottom right. So this is an example transect of one beam elevation collection. So you can see each of these black dots is a detected photon by ISAT-2. And a lot of these are, the system can't tell the difference between surface reflected signal and solar background noise, and the system is very susceptible to solar background noise. But you can, as you see highlighted in the red line, put together the surface that it's measuring, and all of these other detected photons are considered noise. You can see a long track or latitude coverage in the horizontal axis and vertical coverage, vertical elevation on the y-axis. So the surface is extracted here in the geolocated photon point cloud, as we call it. Now, this point cloud of all the geolocated photons, signal, and noise is called ATLO3. That's our level 2 data product that's released to the community. That is the input into higher level products specific to surface, where the algorithms used to filter out the noise and retain the signal are optimized at link scale and reflectance, other parameters to make sure that we're accurately capturing the signal that ISAT-2 is collecting. ATLO 6, 7, 8, those are dedicated to land ice, sea ice, land and vegetation. Atmosphere has its own product, so we can understand vertical cloud structure and extent, or aerosol composition. We look at aggregate data over time. As we collect more and more data, we can expand and provide gridded products. But then the along track products also are available for ocean surfaces as well as inland water. A few of the science I'll get to, but one of my favorites, to be honest, is bathymetry. Now, ISAT-2 uses a green laser wavelength that is known to penetrate water, but no one really thought that 500 kilometers in space would produce much of a bathymeter. But it did. This is one of the first transects that led to the discovery. As you see, the satellite is right over Mexico, and it's traveling, this blue line here, the satellite's going from left to right, and the associated data it's collecting is just beneath in the A-Taylor 3 plot. You can see the satellite travels along toward the coast along this forested hillside. You can see the vegetation in the data. It hits the coast, and you can see that strong signal return from the surface of the water. And then as you get more offshore, you can see the structure of the ocean waves. Then beneath that really calm area, clear area, we can see the seafloor beneath. So we're now getting a global bathymeter that's adding these sea points to other satellite-derived bathymetry products and giving that absolute vertical accuracy that was lacking before. Also really significant in terms of the coverage of ISAT-2 is the ability to map global biomass, in particular the boreal forest, which is a really big contributor to biomass stores as well as changes. And because ISAT is reaching up to 88 north, we're able to capture those canopy heights or tree heights and do highly accurate biomass mapping. This is a recent paper that was released by Laura Duncanson at University of Maryland and is part of the ISAT-2 science team. It's really important to understand time series and the changes that happen in these hot spots of climate change, like ice sheets, the polar ice sheets. This is showing Antarctica, but we can have a similar map over Greenland that's linking ISAT-2 elevations with ISAT, the predecessor elevation. So we get nearly 2 decades of data where we can take those elevation changes, derive volumetric changes or mass loss here. You can see in Antarctica we're getting some slight gains in mass on the eastern edge, but that's balanced, or not even balanced, but overwhelmed by the western side of and also on the peninsula here of mass loss. This was a paper that was released in Science a couple years ago of the first year of on-orbit ISAT-2 collections, also with the ISAT collections previously. Sea ice is a really important indicator of how our climate is changing, and it is certainly important in the radiation modeling of our Earth and certainly water temperature. You can see here what we're interested in is measuring freeboard with ATLAS, and that is the top of the ice flow separation from the mean sea surface, or the lead. That thickness there, the freeboard, then can be used with snow models of snow depth as well as hydrostatic equilibrium assumption, and it can back out thickness. So not only are we seeing where the sea ice extent is changing over monthly cycles, whether it's the freeze period or the melt season, we can also understand the thickness of that ice and how that changes from season to season and year to year. Another neat thing that I thought that wasn't expected, and certainly we don't have a mission product associated with it, but shows the utility of ISAT-2 data, are submarine volcanoes. There's been a lot recently reported of events in our oceans, otherwise not really accessible, if you will, but ISAT-2 has given us a lot of data. So this is in the South Pacific. It was a submerged volcano, and the life cycle of these types of volcanoes is they're submerged, they erupt, and all of the materials from the eruption create a landmass that then slowly, over wave forcing, erodes and goes away, and the cycle starts again. We're able to monitor that erosion process with the ISAT-2 elevations, and we're also able, with the bathymetry capability, to measure the depth changes in the crater lakes and how that relates to the cycle, the global cycle of this process. We've had some recent papers come out about it, and it's just a really interesting application because volcanology was never even considered in the pre-launch phase of the mission, but it's there now. In terms of the life cycle, or lifetime, excuse me, of ISAT-2, we're limited mostly by fuel. Our laser energy stable and is decreasing even less over time than was previously predicted. We're still on the first laser on Atlas, but there is a redundant laser, so we can certainly, if something happens to the first laser or the operational laser, then we can switch gears and go with the backup. Fuel is used to do station keeping and maintain our orbit for precise measurements over specific ground tracks that we have. We do these maneuvers to maintain the orbit, and the frequency of these maneuvers kind of goes with the solar cycle. So what I'm showing here right now, our end of our prime mission, is the red dot on the left, and these two lines are kind of the statistically the bookends of where we might expect that our lifetime will end, knowing that we have to maintain some level of fuel to accommodate a deorbit of the satellite. So we're looking at a timeline from, at the worst case, 2031, at the best case, 2034, but we've got a lot of good years left. Another limiting lifetime component, I guess, is it's getting really crowded up there within the ISAT-2 orbit. This plot is just showing the number of assets there that we need to track and make sure that we don't laze these assets, and we don't want to damage anybody's assets in orbit with the laser, but we also want to do collision avoidance. So that process of tracking objects and avoiding them within the ISAT-2 orbit has become a real full-time job. It also got more complicated by the presence of all of the debris from the Russian anti-satellite missile tests that just put a lot of stuff in there that's not a really controlled orbit, so it's harder to track. This just shows you two orbit parameters, closest approach and furthest approach from the Earth of each of the objects that we're tracking. It seems like we're tracking more than, I don't have the number there, but we're tracking all of these objects to make sure that ISAT-2 is safe, and you can see where its orbit lands right here, kind of in the middle. Some of the bottom lines with ISAT-2 that might be of interest to the audience is the quality of the data. We measure vertically better than 10 centimeters. It depends on the surface, though. If you have a highly dynamic surface, it gets a little bit more complicated, but we're at the centimeter level, and precision is even much within sub-centimeter accuracy. We know where the geolocation is to within 5 meters was the goal. 6.5 meters was the requirement. 5 meters was what we were doing early on orbit, but in many cases we know where the measurement is better than a couple of meters. The footprint diameter is 11 meters. That's much smaller than the 70-meter diameter of ISAT. So again, we're able to resolve much finer features on the surface of the Earth. We can control the pointing to within 45 meters, but again, we've demonstrated that it's actually better than 10, and we repeat these ground tracks within 10 meters as well to understand or contribute to the time series and repeat measurement. Again, thank you for the opportunity. I wish you a great workshop. I'm sorry I'm not there, but I've had fun presenting, and please send me an email if you have questions.
Thank you, Lori. And before to move, Jason has a remark or comment.
Thank you. Just to add to how important these measurements are in these missions, looking at some of these images from ISAT-2, I had the opportunity in my dissertation to participate in Operation Ice Bridge, which was the airborne campaign after ISAT-1 went operational and before ISAT-2 became operational. I did have my dissertation on a glacier called Cermak-Avanarlik, which fed into Jakobshavn, and that was 12 years ago. That glacier largely doesn't exist anymore. And so when you see things like global climate, it's changing before our eyes, and it doesn't just affect the polar regions. It's a global phenomenon.
Thank you, Jason. And also, you saw the concerns about the space debris and how can be impacted in their mission. And now we move to the next speaker, and we conclude this with the last presentation. Is Alfredo Martins. He's an associate professor of the School of Engineering of Report and research coordinator at the NISTEC a Center for Robotics and Autonomous System. His passion for deep sea marine robotics explain why he decided to focus today the talk on the current challenge of underwater technologies and also from deep sea to outer space. Please.
Thank you. Good afternoon to you all. It's a pleasure to be here to be talking a little bit on what we have been doing in underwater robotics and to lay some perspectives of how some of these works maps into the space exploration. As we have been seeing here before, we have been seeing a lot of water, so I'm going to show a little bit more of this water. So first of all, just to point out what we are at INESTEC. So INESTEC is a large research institution in Portugal. In particular, myself, like Ricardo said, I came from the robotics group, Robotics and Autonomous Systems Center, and you have here a picture or a set of pictures that shows more or less what kind of things that we do, that we developed and we operated. So as you can see from these images and some of the ones that I will be showing further on, many of them operate in the water and some of them in the deep sea. When we look from the environment, from the point of view of, and this kind comes from somebody that looks from the perspective of the deep sea and thinking out on using robots in the deep sea, we see that there are some similarities. Obviously, there are a large difference between the space and the extra Earth environment, but basically we have the dimension problem, so huge spaces in terms of area to be covered. We also have aggressive environments for different reasons in many cases, but nevertheless, so they are aggressive environments. They usually, most of the knowledge that we have from outer planets, from the deep space, also from the deep sea, comes from either remote sensing or robotic tools. I know that we have been pushing in for the human presence on space, and this is obviously an effort that we need to push, but the fact is that the farthest object that is today away from Earth is a robotic probe. So basically, these are the tools that now we have to explore this kind of environments. And so these similarities also pose similarities in terms of what techniques, of what applications can be done in terms of robotics. So from our perspective, from the perspective of the Portuguese perspective, clearly we have a huge space. So if we look into the Portuguese Sea, which is a motivation for our work, Portugal is the 111th country in the world in continental area, but in sea area is the 10th. You can see here the expansion of the continental Portuguese shelf, and it's a vast area in the sea, and we don't have resources to be there continuously. So basically, it's a deep sea, it's large, it's diverse, and to be able to be there, we need to have systems that aid us to have our presence. So we have to tackle the deepest operations up to 5,000 meters, 6,000 meters, depending on the point. We have to have the possibility of addressing the space, to do it in a safe way for the humans involved, also in a sustainable way, obviously, and also to deal with the harshness of this environment. When we look for the challenges that we have underwater, I can see here, we can see an images of a mining machine inland cutting stone. And we see that we have challenges in perception. So some things that we took for granted in robotics in land or in the air, like we could take a nice picture, we can see that the kind of images that we can sometimes get underwater. Or we have sensors like sonars that have a very crude view of the environment. For instance, in deep sea, we don't have GPS. So localization and navigation to know where things are, it's something that is difficult to obtain. So how do we address it from the perspective of using robots? For once, we tend to use more robots. So if we have a multi or more systems, we try to work in team, so to speak. So we need to use multiple systems in order to know where we are. We need to improve the perception, either from the perspective of having sensors that give you more information about what you are seeing, what surrounds you, but also to have the capabilities of having understanding better what you are getting information from this. Obviously, there are other points that are crucial. Like I've said before, to have robots in the deep sea, and also in space, obviously, but to have robots in the deep sea is expensive, at least compared to having it on Earth. So the deployment, the access to space, the launch, the recovery. So this is something that obviously is extremely expensive in space, but it's also very expensive for operations at sea. And so if we need to reach high depths, we need to travel with a surface ship to a certain point in the sea where we have access to those depths. So this is something crucial. And typically, when we look at what is the effort doing on the robotics point of view, is how can we reduce the size? How can we reduce the operational cost? How can we increase the quality and the quantity of data that these robots can provide? How can we improve the efficiency from all the aspects of the operation? How can we stay longer there? How can I survive this environment? So, looking at some of the work that we've been addressing, in particular, we've been addressing mainly, here I group it into two areas. One is addressing particular sensing problems, so like tackling problems of how can we work on the perception of the environment, in particular, in this case, starting on the chain of the sensing part of it, and also obviously on how can we use robotic tools to deal with these environments. One of the examples is to use, for instance, and because this is tied with some work that we do in aerial robotics, it's to use to increase the perception, like to use hyperspectral imaging in order to provide you from the air information about marine debris on the surface. In this case, I'm only looking at the surface of the water, but today is crucial to know what's happened with marine litter, in particular plastics. And so this is an example where we use it, a custom-developed aerial drone, manned aircrafts, and a pair of hyperspectral cameras in order to gather information, also to process it in order to detect plastics in sensitive zones. We see an image of Pim Bay in Azores with targets, with plastic targets that are used to be combined this information with the passage of satellites on top of it. So we want this because this is something that robotics can immediately join in the space sector. We can provide in situ measurements that can be used to calibrate information that we can get from remote sensing from space or satellite. Other areas of relevance is addressing, for instance, the lack of biological sensors or biological information sensors to gather information from the space. Obviously, my point of view is, well, we need to develop some of these sensors because we want to incorporate them on robots. So this is an example of, in particular, of doing zooplankton or microscopic imaging or getting eDNA or environmental DNA processing on board of the robots. This increases the capability of the robots of being able to operate in this kind of environments and to have better survivability. So I do not need to operate so much, and so they can stay more time at sea. Other example, which is a sensor that was developed in the context of the usage of robots underwater, but in the raw materials environment. So in order to characterize very harsh and complex and enclosed spaces, is the use of structured laser light systems that can provide you precise information about the morphology of the environment. But this is only possible if we have clear waters, which is something that can vary along depending on the area. But nevertheless, so is something that currently sonar cannot provide you, which is the main typical sensor that is used for underwater perception of the environment for the underwater robots. And also something that was already spoken before by Rui, which is the use of, okay, we have the classical or advanced spectroscopy based tools for mineralogy analysis outside of water. They can even do that at distance, but we are doing an effort to port these technologies to reduce them in size. You see here an example of a LIBS machine that was used to characterize or extract it from a mine, and we try to reduce this to a size and to a technology level that can be integrated in underwater robots. And one of the examples of the possibilities of this is an example of a project that we have were involved with, which was seminal in terms of combining the use of robotics underwater, being able to exploit open pit mine lands. So this is not exploring or mining the undersea. So we have an immense diversity of land mines, open pit mines, as you can see here, a lake with a mineral underwater, and it is very environmentally problematic to extract the water, to mine in open sea, to cut the mine. So if we can extract the mineral without disturbance to the surface, without polluting the environment, we only extract the mine, that can be useful. So this was part of a European project that addressed this in terms of having a commercial system or a quasi-commercial system that's able to do that. And the system is composed by a mining vehicle. So this is a 30-ton robot that is on the bottom of the sea, or in this case on the bottom of the lake, cutting the machine. A dredging system, a surface launch and recovery vessel, and an underwater robot that provides assistance to the system, and also a support vessel. You can see here some images taken from one of the deployments. In this case is in Limur mine in the UK. So you can see here the support barge and the mining machine being deployed. And you can see here a set of sensors put it on the mining machine that allows this mining machine to have information about the environment. In this case, we have an operator, so because we have a pipeline that brings the ore to the surface. But nevertheless, the problems of perception of underwater still are a problem here. So we want to know the exact location of everything. We want to know how much rock are we cutting. We want to gather this information, fuse that together, and provide a digital twin, provide a virtual environment that we can see here, in this case, where all the information from the different sensors, either from the sensors mounting on the machine, either from the sensors provided by the additional robot, can tell you what you are doing, how the environment is changing, and the difference is between the operator looking at an image like this or having a 3D environment model that says and precisely tells you what is happening. So this is an example of some pictures of our AUV when it is at surface, because underwater we don't have images of it, but this type of robots can provide you accurate information for the operation. Another example of even more tricky operation is how can we explore deep underground boreholes, shafts, up to, in this case with this robot, up to 1,500 meters. So this is already at sea, it is deep sea. And how can we explore this in a very challenging information? Just to show why this is interesting, in Europe we have more than 30,000 mines that have been closed. So they have been closed, but because nowadays Europe is not a mining region for many reasons, either for environmental reasons, either from economic point of view visions. But we need to know how they are. We had the tests, for instance, in Idrija mine in Slovakia, where it is an abandoned or a closed mercury mine, one of the largest in the world. And there's a city on top of it. So we need to know how's the state of the open mine, independently of not being operated. So there are many reasons why we want to know this kind of information about these mines. So this is a critical environment because it is deep, it is very unstructured. So you have a lot of, you can have mines with clear water and mines where you cannot see a centimeter. You can have mines full of garbage. We can have mines that are collapsed, mines that have large tunnels, to mines that have passages that were built in the Middle Ages. So this kind of environment is really hard from the robotics point of view. So, but we think robotics can help. How? Like this.
Prometheus,
this is what we want to do.
We are now mapping.
We have a robot that we drop in the mine, and the robot builds a map. Well, we don't have that. We have this. We have a robot which is a little bit bigger that works in the mine and operates in this area. So this has been a continuous effort addressed by together. We have already operated in a lot of sites in Europe by a consortium that basically has the technology part. So we have been developing the robot and partners from the geology and the mining industry. So in this case,
the initiative to discoveries as the structural details of the cave start to appear on the monitors. The known part of the Molnar János cave is 7 kilometers long, but who knows how many meters are hiding below the maze-like structure makes it hard to find the continuations, but the geological information can help us in the search for new passages. The formation of caves follow the pattern of faults, cracks, and fissures in the bedrock. The directions of these features determine the directions of the passages. With the sensors of the robot, we can record the structural geological marks on the cave walls, and later the main directions can be calculated, giving hints for further explorations.
Environment. For the deep sea support, I want just to briefly point out 2 areas of research and development. One of them is to improve the presence on deep sea through autonomous underwater vehicle docking and energy transfer and communication. So if we have the possibility of continuously leaving a AUV, an autonomous underwater robot, in the environment, recharging by itself and coming back and providing data, so we increase the system operation. So I do not need to answer the question, how many hours does your battery survive? It survives the ones that needs to recharge itself. So this is one effort, and also increasing in this area is the developing of the possibility of having robotic deep sea landers. So these are systems, you can see them in the lab. We have them in the lab. So these are systems that deep sea. So how we are adding? So this is the final slide, just to tranquilize the event. So in terms of globally, how is the community advancing in terms of deep sea robotics? So basically, it's been addressing in 2 ways: increasing the TRL level and reducing size. If you look at the history of underwater robots, when we usually said, oh, it's an AUV, autonomous underwater vehicle, everybody would think something big, deployed in a crane, in a big ship. So nowadays, the towards is to use small things, smaller things, at higher depth. And we are addressing this also. The other is increasing the permanence at sea, either by having infrastructures or flexible infrastructure, something that I can go with a low operational cost and drop it there, and then I can recover easily. So this is something. And also addressing the perception problem. So like I've said usually to some of my students are here, most of the problems in robotics are perception, is to know what's happening with me, what's happening with the world. So some points of how can I make immediate parallelism between our robots and space. I have here some pictures of, I have a problem. The turtle robots need to land on the sea, on the seabed, safely. So they have sensors. They must decide autonomously because I will not be there to guide them to choose a spot. This is the same problem that I can have when I land a lander on Mars. So there's huge delay between Mars and land. It's not possible to have somebody looking with the joystick, looking at the screen and saying, okay, let's move a little bit further left because I'm going to crash. So we can have underwater navigation needs support. I need support systems in order to navigate. I need to do the same outside because I don't have global navigation systems. So there is a parallelism on what we can do in the deep sea and what we can do in space. So to conclude, this is my final take, is that we have somewhat similar problems. Obviously, we don't have the excessive pressure on space like we have on deep sea. We have the reverse of that. We don't have, many cases, we don't have the problems of temperature. We have other problems of temperature, but they are clearly not the same. We have different types of problems in communications, but many of the problems of perception, of control, of addressing the unknown and to be able to be there are similar. And so a lot of developments can be done between the deep sea area or the underwater area and the space exploration. So this is, and then obviously I would love to bring one of my robots to Europa or Ganymede and explore the sea there. So if we have a lot of water outside, so why not bring a UV there? Okay, thank you all.
Thank you, Alfredo. And I think we have now a Q&A, not 10 minutes, not 20 minutes, probably 1-2 minutes. If you want to address one question, there are questions there. Microphone, please. We are very close to the conclusion, so yeah.
So I would like to ask you mentioned that you are planning to develop in the future some sensors for the biology. How it will actually work? What you are going to... Okay.
It works.
So basically we are doing a stages approach. So in the terms of ADNA, which is probably what you're addressing, so we did this first stage. So typically when the marine biology do studies of eDNA or DNA, they use what is technically called the Niskin bottle. So you go to a place, you bring 5 liters, 3 liters of water from something, and then you bring it to the lab, and then you process it to the whole steps. So you filtrate it, you do the PCR, and so all that stuff, and then you, in the end, it potentially sequence the information. So what we are doing now, first of all, we already developed the first initial steps, like for instance the filtration step in a certified process that basically transfers this part of steps from the lab to the place. So it seems, for instance, instead of bringing 16 bottles of water, I bring, at this stage, I can bring 16 samples of DNA, filtrated DNA, already with preserving fluid. But we are still doing more things, more steps. So we are doing lysing, which is breaking the cells in order to gather the information from the DNA, to extract the information. And we are doing, this is something that we are doing right now. So this is our immediate step. So it is to incorporate the DNA purification and some part of the replication on board. So this is the step number 2. So my global aim in the future is, okay, I will have a system, a sensor, one of those cylinders that you saw there, when I will filtrate water in a point. Then after that, I will start to do all the steps that usually are done on the lab, ending up in a final sample that can be sequenced. So traditionally, this part would be, okay, the sequencer is something like a big machine in a big laboratory. So currently, there is already some sequencing machines with reduced space. Obviously, for us, the difference between my perspective of reduced and the perspective of the manufacturer is still somewhat disagreeable. But clearly, it will be possible in near future to integrate some of this, and so to have the old pipeline, at least having the complete pipeline. Another thing is what we will do with the data, and obviously, there are lots of problems to solve between this. In fact, there are already some, for instance, the Embry Research Institute in the US already has a certain type of system that does some parts of it. So basically, this is something that is possible to be done. Mainly because the advances, mainly the medical industry advances that usually push for the getting reduced costs in sampling, reducing costs in sequencing, improving procedures of getting more information for more corrupted DNA samples. This is pushing us, so the industry is moving in our favor. So I can count that today's DNA sampler that is this size, or DNA analyzer that is this size, can be this size, because I'm sure they will get it. They will not build it for me, they will build it for blood droplets, but the industry is moving in that direction. So I plan to find them in the middle way.
This is really, really cool. Thank you. Can you let me know when you will be done with these experiments, and maybe we could do something interesting?
Sure.
Very, 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 very interesting. Thank you.
One more question, really fast. 5 seconds, like the microphone, okay? That you
test. Okay. So I have 3 questions actually.
3.
So the first one was, how does the spherical robot you've shown compare to a traditional AUV? The second, what is the...
Sorry, just to let you know, we can only do one more. We have 1 minute. So,
Okay.
so choose your top priority.
All right.
Thank you.
So what would you say is the state of the art regarding the miniaturization of vehicles while maintaining control in underwater conditions? Because you have the waves and all these dynamics. So, and you have shown a very small example from a movie. So how would you achieve that? What is the direction to that?
So regarding the spherical shape of robots, so the main issue of the spherical shape is to be able to operate in an environment without getting entangled, to have full 6 degrees of freedom control. So basically it rotates everywhere like a full actuated satellite. So it has motors in all directions, and it also has an internal pendulum that allows it to have a steady state configuration. So basically, if I need to go down a slope in a corridor, I will trim the vehicle in that direction, and I will not spend energy to move forward and backwards. So in terms of control, this is the main difference, is because it's developed in order to be capable to operate in very tight and in close environments. And if you are saying, what is the state of the art of miniaturization? Well, that robot is probably the state of the art of miniaturization. I know that this is something like, well, this guy is bragging a lot. Why? Because obviously you can have smaller robots. But if you have smaller robots, you cannot have the same sensors. For instance, you cannot have a robot like this that can move during 5 hours, come back to the same point, and lose 10 centimeters in navigation. You can have an underwater robot this size, but then the robot simply doesn't know where it is. You cannot use it, for instance, for mapping. You put some kind of sensor, the robot is moving, but it doesn't know where it is, so it doesn't know what it's seeing. So this is a trade-off. If you go to the literature, or if you want to buy an AUV for 1,500 for 1,000 meters depth, it's going to be big. And when I said, well, they used to be big, yeah, it used to be much bigger. So when we talk about how's the weight from a vehicle for 1,000 meters depth, well, it's on the order of tons, not 90 kilograms. So this is the difference. But it's possible to have smaller vehicles, but they don't know where they are.
Shall we conclude? And then the final words, Yvette, then to pass to Professor Luisa. There are several topics in several dimensions that we discuss here today, and particularly from oceans to Earth, and also looking up to space. And we talk about georobotics, space resources, space medicine, remote sensing, microgravity, and we saw nice movies. Thank you for that. And also talking to take care about our planet. And of course, we finish our conversation here with Alfred about how difficult it is, the deep sea, and some kind of, we can compare to the outer space. Yvette.
Okay. Also, that we have a time and a place where we're privileged to have all these platforms. I think it isn't by accident that we have so in deep space, microgravity, neutral buoyancy, that we have space medicine coming together, and that we take opportunity with that here. So I'm really grateful to see that we have an interconnected, we call it the ecosystem, but it really is this interconnected existence that we're all traveling together, we're all exploring and discovering together. And now in this room, I know you're eager to ask more questions. The privilege of being here is that we can talk to each other and we stay connected. So I hope that that's what comes of this.
While our discussants get ready for the next roundtable, we'll watch a recorded video from Kelly Girardi. Kelly is a researcher at the International Institute for Astronautical Sciences and a payload specialist at Virgin Galactica, and will soon take part in a suborbital flight. Kelly, tell us what you've been up to.
Hi everyone, my name is Kelly Girardi, and I'm a bioastronautics researcher with the International Institute for Astronautical Sciences. I'm going to be flying on a dedicated research mission next year with Virgin Galactic, where I'll have the opportunity to test some of the technologies that we've worked with here on Earth in space, and I am so honored by the opportunity. This is something that we've been working towards as a research organization for years. We've made use extensively of parabolic flight campaigns here on Earth to help us mature technology and advance the next generation of space technologies, but we have always endeavored to actually take our researchers and our research in the unique environment of space where we can benefit from longer duration microgravity exposures. So I am beyond honored to have the opportunity to do that. One of the pieces of research that I'll be bringing to space with me is the Astroskin Biomonitor Wearable Sensor System. It was developed by Canadian company Carre Technologies with the support of the Canadian Space Agency. And it's essentially a smart garment that is worn underneath the flight suit, and it will be collecting biometric data related to how my body responds to spaceflight. The Astroskin is currently worn by astronauts on the International Space Station, collecting a variety of biometric data, but my flight will be the first time that we're able to collect data during launch, re-entry, and landing as well. So I'm really excited to contribute to novel data collection. I really believe that we are on the doorstep to the next golden age of space exploration, and I'm so excited about the potential of novel spaceflight platforms and suborbital providers like Virgin Galactic to continue to usher this in, to provide affordable, repeatable access to space And not only for researchers, but also for civilians of all disciplines. Space is our shared past and our shared future as a species. You know, the first few hundred flights to space had to focus entirely on function, but we're at the point now where we can optimize on experience as well. And I'm so excited to see poets, to see athletes, to see musicians, to see civilians from all disciplines experiencing the wonder of spaceflight, the perspective of seeing Earth from space, and bringing that back to our home planet. I think we'll all be a lot better off for it. And of course, I'm excited for the next generation of science and research that's going to be enabled by this next generation of responsive platforms. Suborbital spaceflight is a great equalizer for access to space, and this is just the beginning. So best of luck at your workshop. Thank you so much for letting me take a few minutes of your time, and I'm so excited to see what's in store for all of us, and particularly for Portugal as an emerging space nation. I think this is the beginning of the next greatest chapter in space history, and I'm so excited that we all have front row seats to the final frontier. So thank you so much.
It seems we are ready to start our last thematic session. I'm pleased to introduce to you our roundtable moderator, Luisa Bastos. Luisa is the head of the Ocean Dynamics Coastal and Water Systems Research Group at the Interdisciplinary Center of Marine and Environmental Research, CIMAR, and has been serving as Area Director for Space Earth Interactions on the UT Austin Portugal program since 2018. Luisa, thank you for accepting our invitation to guide this conversation with today's discussants, Yvette Gonçalves, Ricardo Conde, Aaron Pressard, and Miguel Gonçalves.
So, good afternoon again to everybody. I start by thanking the participants in this roundtable. And I will skip the bio introductions because you all know them. They were already introduced and we are out of time also. So I would like to take the opportunity of this video from Kelly, from Virgin Galactic, to start by launching the theme related to democratization of space. And so we are assisting, as it was mentioned before in some talks, the new space. And the new space is driving a revolution in the space sector. And like never before, private companies, private industries are paving the way for space now. And either by exploring new services or by developing and deploying new systems and making the way for more fancy opportunities like the tourism, space tourism, and also related maybe with space debris and asteroid mining, or maybe other opportunities there. So I would like to some comments from my colleagues of the roundtable on the opportunities that they see. We have challenges and we have opportunities, of course, here. And I would like to hear some comments, maybe all of you or some of you who would like to say something. There always.
Opportunities. That was the question. Well, I work in science communication, so communication is a key part of my life. And we didn't speak a lot about communication in this workshop. And it's especially important because last week it was published a major study. 20,000 people were survived in 11 countries about the perception that society has about space exploration. And it was unveiled by Inmarsat, a global mobile satellite communications provider. And, well, at the beginning I thought, well, here it is, another study that says space is great, space is huge, space is fantastic, and people that don't belong to this industry are certainly amazed by space. But the results were nothing what I was expecting. For instance, one of the conclusions was that the society thinks about space, it's like sci-fi, science fiction, and they don't recognize the potential that space brings in our life. And so I'm going to share with you just one of the numbers and one of the questions that were made to these 20,000 people. And so they asked them, what do you believe? Do you believe these industries could function without space? So they had to identify industries that don't need space. And so 66% said retail, 54% mining and construction, 52% agriculture and farming. As we know, all of these activities are strongly dependent about space, strongly. And so we cannot pretend that this study doesn't exist, and we must accept that also in space exploration, we live in the new space era, but maybe we have to acknowledge that we need a new space education and communication.
I actually wanted to piggyback because I think it's important that all of us here in this room are here because we were informed. We had the right to information, we had access to information. Those online have a satellite connection to internet so that they can be online, and they were privileged to know about this. There is a very important bridge from what you just mentioned, from living your life on a day-to-day basis in a place that might be marginalized, might be forgotten, not represented, to connecting it to those of us in this room and online today. And that is, science communication isn't for entertainment value only. I think the mic is on. It's not for entertainment value only. It is important that it is entertaining for some, but it is to allow access to information that some of us who hold the information are in an exceptional position to have. And to be aware of that. We all have our technologies. I mean, today I wasn't aware of the underwater robotics. I'm aware that it exists, but to learn from him today makes me excited. I might even change my career because I was exposed to that. And that might revolutionize a new invention, but you don't know because I didn't know before. And so I think when we communicate what space has as relevant to Earth, it is also a reminder that there are over 1,700 registered inventions that came from the space industry that we use every day. You have canned food in your kitchen. You don't get botulism and die from it because space programs developed safety measures around that food. You can test the temperature in your ear at home without going to a doctor because there were sensors and technology that was needed for space, and so we adapted that for Earth, and on and on and on and on. If we can do a better job of sharing that knowledge and how, I mean, I'm holding my phone here for notes, but this phone only works because it's connected to something. Otherwise, it's a box in my hand, it's plastic. So I think that it's an important thing to have and I would say science communicators communicating our technology in really creative ways so that people understand they're part of what's happening. It matters.
We We had a pandemic. Well, we still have a pandemic. And one of the precious lessons that we should learn about these pandemics was the importance of science communication. And what excuse me for being so dramatic, I think that Portugal, and with my program, it's the only public live TV magazine about space exploration and astronomy in Europe, at least in Europe. Every time I go to a school to communicate and to see those bright students anxiously waiting for to know about the cosmos, often I have teachers saying that, well, I'm so glad you are here because they ask questions that we don't know how to answer them. And I know that the topics about astronomy are being removed from the educational curriculum because there is no effort to update teachers about the new developments. So that's why in this kind of events, I always try to push about this kind of difficulties and ask to everyone who is watching me, hearing me, why is this important? Even for the private sector, are they interested in science communication? That's a question that I take it to you.
Luis, let me point out one thing which is important, and particularly with the challenge that we have today. And when we discuss about space, there are several dimensions. One is the knowledge, of course, Miguel, and this is an inspiration for the young generations. And this is normally the perspective that we have from space. I will give you an example. Space is every day in our lives. Look, if you go to your mobile, this is plenty of space here. The thing is, this becomes a commodity. That means nobody cares if you use the space or not. To ask for a Uber here, we are using GNSS navigation signals, right? This is space. Probably if we make a call for Antarctic or Arctic regions, we are using space. This is the good news. If space becomes a commodity, that means it works. The thing is, the more visible size of or side of space. And this is particular today, space must deliver and must tackle the problems that we have on Earth, in particular with the climate change. Alfred presents a big, huge extension of our economic region, the maritime region. There are no other ways to monitoring, particularly the resources, particularly the dynamics, interactions between the oceans and the climate change, without having some kind of satellite sensors, right? So this is one thing. Satellites must deliver, must be address the problems that we are living today. One thing, one of the main problems that we have on the climate change, it's all about the land and maritime areas. Climate change are these two things, the land management and maritime management is one of, let's say, the routes that we can tackle to change and to work in the climate change. And these two dimensions, it will only be possible with the data from satellites. The thing is, what are the barriers that we have today? Look, nobody pays with the GNSS data. You don't pay for to receive GPS or Galileo here. But if you want to develop some application and also ask to your application here, how is the Earth today? What is the carbon mapping that I need to understand in the north of country? What is the carbon stock in the north of the country? This is not possible because there are some barriers. Now, this is the problem. We need to have the same data policy for the GNSS data, also for the Earth observation data. And this is the barriers that you need to tackle. So space must deliver, must have some kind of answers to tackle the real problems. Space must be on the fire prevention, erosion of coastal areas, must be in the lack of water, also to manage our biomass. And this is probably the visible part of space.
Check. So the question of space, it's been really interesting to see last year, around this time, Blue Origin had a couple of flights back to back. And what we saw last year was the youngest person to ever fly into space. I'm talking like cross the 100-kilometer altitude. And a few weeks later, or perhaps even on the same flight, the oldest person to have ever flown. And what that brings to mind, Kelly gave her talk here, even 5 years ago, it would be impossible for me to think that opportunities existed for such people to fly. And now that those opportunities exist, we're at an edge here where we don't know where this could lead. But I'm excited. I'm excited to think that what was once a tremendous barrier to have an opportunity to fly as a government astronaut, now that barrier, it's still there for those astronaut programs, but there's this parallel track where the barrier is lowered. Right now it's tied to how much you can afford to pay, but the trend is that that's coming lower and lower and lower. And I'm excited. I'm excited that all of us have a potential opportunity to go up there, whereas, 5 years ago, probably we wouldn't have thought we would have had a chance. So I can't predict what it's going to look like in the future, but what I do anticipate is that things are going to be very different, and I would love to see a situation where flying to space is as commonplace as taking an airline flight. And in the early days of test flight engineering, you had to be the fit of the fit, right, to be a test pilot. Now, to board your plane, you don't have to submit a medical exam, you just buy your ticket and go. And it's the same idea for space. In order to fly to space, with the government programs, you're top of the top in terms of physical health and so on. And I think what we're seeing is a model that's shifting, questioning, is that really necessary for someone to fly?
And this will have a tremendous impact also in environmental monitoring. And this is still something that we will see in the future, because this will complement the space, the remote sensing, and this will be for sure a tremendous improvement. Yes. Yes.
Will rely on that I mentioned before about the scenarios for the space economy. Look at this perspective. If we will have a new constellation to provide new kind of services, normally is provided is an institutional service, like look, Galileo and GPS, they are institutional providers, right? But if we are going the directions to provide this kind of service to the private sector, we enter into another level of complexity, because look, the precision carriers for the navigation is classified. It's something that should be regulated. How we do it with the private sector to supply that? This is a challenge. This is the same that we are providing, for example, very high resolution, and now it's coming very high resolution satellite constellations that this will impact for the privacy, our privacy, and particularly if we get resolutions for very, very low Earth orbit, 200 kilometers with air breathing altitude control satellite, then we enter in the 10 centimeters. And then there's rise another awareness about privacy, right? And also sovereignty. It's a national threat to the defense, and so this depends out the way what kind of scenario that we will be facing in the near future. And probably the military sector will have a word to say.
I just remind that when I started to use GPS a long time ago, I must not tell how much, but it was more than 30 years ago. There was this concern from some developing countries. They don't want us to put their a GPS receiver at that time for military reasons. But in fact, this technology is there, and this calls for also the need for regulatory framework for to avoid exactly that the society adaptation to these new technologies is overtaken by the technology acceleration, which in fact, for example, we have seen with social media. This is happening at the moment. So, I don't know.
And I'll just make a comment, sorry, if I can. I think we forget, as with maritime, with flight, air flight, with almost any industry, technology, I won't say always, but often supersedes policy, right? So the technology comes first, and then we learn what policies we need to put in place, and then that's the hard part, yes? And so we're in that, you mentioned this earlier, we're in that space where we are now catching up to our behavior in space. We created the technology, we launched it, we orbited it, now what? And then we have to collaborate internationally. What's in the best interest of every country, every commercial provider, and what is it that we can do to work together, and will we find that?
We are living this moment with space traffic management. The technology is there, but the rocket science is how to put all the countries in a frame agreement. So it's more complex, the space law, than particularly the technology.
That's not necessarily good, isn't it? Technology going in front of politics. I believe that we have to throw a little bit of cold water to this subject. I mean, we had just a few days ago NASA administrator saying that he fears that China is going to occupy the moon. That happens for a lot of reasons. I don't agree with him, okay? But it's technology talking first. It's the lack of law, space law, talking then. And I think that's not necessarily good, technology going in front of politics. We need regulation. We need regulation.
But we still have open waters. You know what I mean? We have regional waters and we have open waters in our globe. That means it doesn't belong to nobody.
So in my generation, with using all of this latest technology that is enabled a lot by the space technology, comes the question of, we talk about privacy, but there's also the question of hacking, just to summarize it all. And when we think of ground stations communicating with satellites, there has been concern about how do you secure those communication networks? How do you prevent someone from gaining access to your satellite in a malicious way? And this question of policy, technology, and so on, as a person who straddles that world, as a research scientist, sometimes it can be frustrating because of the one thing, which is time. The technology is ready to go, but we have to wait for policy to tell us what we can and cannot do. And the people that are making the decisions for policy sometimes don't know what the technology is about. I think of an example where in the US, a politician was describing some policies for the internet, and his language was, the internet is not a truck, it's a series of tubes. And as a young person, I'm like, is that the best person to be making policy decisions about the internet? You know?
I think that the problem you said, technology can come first, is that the technological acceleration is now much higher, and it will even be more. And so it's quite difficult to... It's because we have both microphones. Okay. Don't know. So this is a problem from this point of view.
Okay. When you said like your generation, I guess that's my generation. I'm Generation X. I don't know if there's any others here. I was born the year the Voyagers were launched. And so 1977, I, of course, didn't know that's when they were launched. But my experience growing up in the space discovery age, I didn't know as a child that the first photos of every planet that were coming in were the first photos. I was being taught that space was, not that it was being discovered, it just was, that it was the knowledge that existed, and I accepted that as a child as fact. And I was excited, and I was inspired, and I was on those geological trips into the mountains. I was in the robotics club because I just thought it always was. So the power of technology was very vivid for my generation. And we had access to Star Trek. And I thought that I could be on Star Trek. I went with Dr. Reimuller and Aaron to the Star Trek Museum. And it was vivid for me why I believe in space, because I watched it. I believed it. And this generation, I think you have the opportunity not just to watch it and believe it, but you're creating it in a way that we didn't even have access to that technology. Like he was showing us his last technology. What? Those are the questions that make me happy to still be curious.
I will say to Yvette's point, to everyone here, the opportunity is available for you to access space, whether it's a payload or you find a way to get funding. Like NASA is funding people to go to space. They have call for proposals. Show us a reason why this experiment needs to be done by somebody in space. And if it gets selected, you get funded to fly on a suborbital mission. Anybody. They're not asking you to be an astronaut program. So opportunities are out there. Find them. And don't let the new space 2.0 pass you by. Don't read about it in a newspaper. Go ahead and make it happen.
And appreciate the power of the storytelling. The storytelling. Because we live, even in science communication, in a time of instantaneous discovery. We present the final result. We don't talk about, well, I only have 10 minutes to speak about the cosmos in public television, so I don't have the time to tell the whole story. But it's astonishingly important to make storytelling about how are we going to Mars? It's not just about the first step. I found it very interesting that I was invited by Mr. Ricardo Conte from Portuguese Space Agency to be in the final jury of the contest that he mentioned, in which we had to interview 60 students, young students, and to choose 30 to do the parabolic flight. And it was a profoundly moving experience that I had. And the final question that we made to all of the students was, imagine that you are the student, that you are the astronaut chosen to be the first one to make the first step in Mars. They all were terrified by that question, because we asked them, what would be your first phrase, the first words in Mars? There isn't any wrong or right answer to this question. What we wanted to know was if they were valuing the individual experience or the collective, the humanity experience. Funny, most of them started to express their personal voyage, and then they remember, oh, but I am here to represent humanity. And some of them told this precious thing, I am here due to the effort of thousands and thousands of people. That's storytelling too. It's kind of marketing too, but it's necessary marketing in space. And I hope that Ricardo don't take me wrong, or my colleagues at Ciencia Viva, because the winners are going to be announced tomorrow. Let me share with you a small confidence, and I finish here.
Don't say the names, please.
I'm not going to say names. I'm not going to say names, but just take a look at this curiosity. We asked them what they wanted to follow, what they want to be in the future. Well, 80 to 90% said they want to go to aeronautic engineering. I was glad. I was glad. And in 60 students, we had just one student from humanities. Her background wasn't science. Her background was language and philosophy and history and economics and so on. And we asked this girl, what do you want to follow? And she said, law. Maybe space law, because there is an absence of that. And you know what? She was the winner of the contest.
So I just want to make a small comment. Talking about the storytelling, that's very much a human element. You know, you can have a rover land on Mars, on the moon, but that rover cannot tell you that experience, that passion. Now, there's a role for robotics, and I'm not putting it down at all. Very important. But sometimes that human element, just to tell that story and to communicate what that feels like, that heart to heart, it's the storytelling. And it's just so valuable, and it's worth sometimes putting a person there versus the robot, but I love robots.
Do you know who is the best ambassador of, right now, of space and space tourism and so on? It's Captain Kirk. Bill Shatner went in a Blue Origin flight, and when he came back to Earth, he was in tears. The psychologists say that that's the overview effect. The notion that we have a delicate planet. And his words were heard in all continents. His tears were the tears of those of us that want to go up.
Let me just, this is a final, 30 seconds, I'll spend 5. Remember when I said about this big challenge about our planet? This is something that we need to be concerned. It's a big problem that we are facing. And the only way to know more about these interactions are very complex. Remember, I showed you that video about all the streams, the oceans. This is a very unique world. And to better understand that, satellites play an important role to get this more and more data, to get an approach to the new real-time planets, the digital twins, for oceans, for atmosphere, for interactions. And what we are now thinking, all of us for sure, is the heritage, the legacy that we will give to our kids. I have 57 years old. I know that this is the moment that you say, just like that. But I remember my parents put me in the perspective of the better world. I could dream to a better world. And my daughters, I have 2 daughters, I will say the names, Caroline and Beatrice, I'm so proud. And she cannot dream about that. She are concerned about recycle. She are concerned about the lack of water, the lack of foods, probably scarcity, and also lack of oxygen. So how can dream? This is really urgent to think and to take measures. And the only thing that I conclude here is to know when science and technology, fundamental science and developed technologies can give these answers. Remember the COVID. We looked to the science. It was a science moment. I remember in our news, our ministers looking to each corner to see if there are some answers for the science. And we did that, right? But we cannot always to wash our hands and say everything will be okay. We need to really do something. This is a step-by-step problem that we are facing. And when we wake up, in 10 years, it will be too late. And the question of energy is one of the things that will put ourselves in the path to the green society. And it's time to really take the perception, to have the perception again, that the energy is the key drive to our decisions to have a better planet. And we don't need to have some kind of taboos to discuss gas, nuclear power, because it's part of the equation. And if we put taboos in this discussion, we cannot find in the upcoming years some kind of alternative to fight against this problem. Thank you. I take more than 30 seconds, right?
Try to wrap up a bit and finish this. So it's too high. So taking the words of the last speakers and also other speakers here, I think that we have heard here about how space exploration is impacting society and humankind even. And to start with, the perception of the fragility of our planet, like Ricardo stressed, and this sense of interconnectivity on the ecosystems and environment. And new visions in the ocean exploration and exploitation. Also, we have heard about this. And a real revolution on the way we move, interact, communicate on the Earth and beyond. And also other aspects that have to do with the knowledge of our body and making health better. It are also important things. And there was a reference to China and the moon station. We must think if we must look at space with in a different approach, like we do at Earth, concerning borders, and also or otherwise, maybe we are returning to the space race and to the Cold War, which is not good. So we have security problems. Also, that the space opens. It can open significant security problems. So we also have to act on that. And we have to dream that space will become our common ground and a safe haven. So I thank you to the participants of this roundtable. It was my pleasure to be here, and I thank the organization for inviting me. I have learned a lot with this, and we really have to finish. Otherwise, Anna will throw a spaceship to take us away. Okay.
Thank you, Louisa, for moderating this insightful roundtable. We are about to wrap up today's workshop. For the closing speech, let's welcome on stage José Manuel Mendonça, Chairman of the Board of Finesc and National Director of the UT Austin Portugal program.
Good afternoon. Now, I'm going to be brief because I know that just me between you and the drinks. So, good afternoon to you all. So much I have learned today. I came here with the idea that I was going to be here and making some phone calls and working at the site in parallel. But finally, I would say 90% following the workshop, which is not usual. I'd like to leave a special salute to our host, Maria João Viamonte, President of ISEP, the School of Engineering of Porto Polytechnical School, and also Ricardo Conde, President of Portugal Space, and all to greet all of you. And thank you for your present and valuable contribution of the speakers and discussants. Just a word to someone that came in and out very briefly, Manuel Leitor, the former Minister for Science and Technology and Higher Education, which was the visionary both for Portugal Space, pushing it hard, and also for the UT Austin Portugal program. Allow me for a first word of contextualization of Portugal, Europe, and international partnerships in science and innovation. I'm going to begin by citing a researcher of the Gulbenkian Foundation, Felix Ribeiro, who is an expert in geopolitics, with a metaphor about Europe and the international arena for the last decades. He said that China is our factory, cheap labor, offshoring operations in our global chains and manufacturing cheap products. Russia is our gas station, cheaper energy than we would have anyway. US is our police department, ensuring our security without spending too much money in Europe with defense. And we, Europe, we have been sitting in the sofa. As well, you know, this is no longer possible. But there is more. You certainly heard about the Bilderberg Group, started in 1954 after the Second World War. It's a kind of dialogue forum between Europe and North America, through meetings with high-level politicians, experts in industry, scientists, academia, and media also. The aim was to prevent another world war after Second World War. In June 2002 in Washington, in their meeting, the agenda covered critical issues like geopolitical realignment, energy security, sustainability, post-pandemic health, but also China-US technology competition, Europe is out, and trade and deglobalization. All these global challenges, as the quest for green, digital, and healthy societies through science-based innovation is a global challenge calling for global solutions. And that's why the word deglobalization is threatening, because we cannot deglobalize the global challenges. So deglobalization is also threatening for the development of science and science-based innovation. We have been living in a paradigm where innovation is both local and global, depending on business models and value chains, but science is definitely global. Science is borderless. Science has no frontiers. The scientific development cannot be cramped into economic and political blocks. That would be an unacceptable setback for humanity. So, what can we do to fight deglobalization in science and innovation? And this workshop is certainly a great example of what we can do. This workshop is a collaboration between INESC-TEC, the Austin Portugal program, the International Institute for Aeronautical Sciences, Space for All Nations, the School of Engineering of Polytechnical Institute of Porto, Faculty of Science, University of Porto, and the Portuguese Space Agency. And one of the main goals was to build bridges between different stakeholders taking space exploration in the unifying team, a team that convokes many fields of knowledge, robotics, astronomy, space medicine, geology, space research. We have seen it all. A theme that cannot be approached without understanding Earth, water, and underwater systems, on relying also on international partnerships. The panel of speakers and the many experts who accepted to record the message have been very clear that the race for space exploration is well and truly underway and mobilizing many disciplines and sectors. These exciting times require, however, orchestrated actions, accountability of actors, including nations and their governments, and the willingness to commit to shared governance of space. Space for all nations, but how? How do we broaden access to space and space technologies without compromising its sustainability as well as that of the Earth? So this event is the first of one outcome of the MAU signed this year between the Portuguese partners in ESCTEC, PT Space, ISEP, and FCUP, and the International Institute of Aeronautical Sciences. So this MOU attests the importance of international collaboration for the benefit of humankind. It supports several actions, and it helps Portugal to be an emergent space agent, to have a more prominent role in shaping the future of the space ecosystems. The Austin Portugal, as UT Austin Portugal National Director, I must not overlook the program's contribution to the production of science-based knowledge on space-Earth interactions. This scientific area has been committed to unlocking the full potential of integrating spaceborne, airborne, marine-borne, along with underwater data towards a better understanding of the ocean, including deep-sea areas and its interactions with Earth and atmosphere, aiming to improve predictive capabilities under climate change scenarios. Finally, I emphasize these are exciting times for us all, and particularly for the Portuguese research and innovation community. Our country has been bustling with several international space, ocean, Earth-related events recently. We had the UN Ocean Conference in Lisbon 1 week ago. The GLEX Summit is happening this week in Azores. The 2022 edition of Space Studies program elected the city of Oeiras to expose participants to new perspectives on the world's space activities. So Portugal is moving. Because of the future of the space is now, is of the utmost importance to accommodate space in our strategy, strengthen our network of partners, and build a roadmap combining both low-hanging fruit with more ambitious goals. To close, I would very much acknowledge the speakers, the event supporters and sponsors, as well as the scientific coordination and local organization team. And of course, once again, our partner and host, ISEP. Enjoy the drinks because you deserve them. Thank you very much.
Dear all, we must end our live session from ISEP. It was a pleasure to have you on board. For those in the auditorium, we'll start our Space Robotics Sunset in a few minutes at INESTEC's Laboratory for Robotics and Autonomous Systems. You're all invited in. You'll also get the chance to attend a technological exhibition where you can continue networking and talking about the future of space exploration, technology, and robotics. Please follow our staff. SOE Space, Ocean, and Earth Insights workshop will certainly come back next year for more knowledge sharing. Thank you. Until the next time.